Hi everyone, good morning. So let's start now. Just give me a second. Okay, so let's start now. In this lecture, we will study. In the last lecture, we have already seen the planar graph, correct? So did you watch that video? Did you watch that lecture, planar graph? Did you watch it? Because this is very important, okay? In that lecture, I have already told you all about planar graph, okay? Karthik, did you watch chromatic number? See, Karthik, in this lecture, whatever we study, that needs previous knowledge. Okay. So this planar graph we have already seen in the last lecture. I uploaded one video. I recorded one video. I uploaded one recorded video. So in that video, planar graph is covered. Okay. So before we start, let me know anyone did you understand planar graph? Did you understand that video? I have told you all about planar graph. What is a planar graph? What is phase? What is degree of a phase? The theorem, Euler theorem, the proof of Euler theorem. The proof is not important, but small statements are important. Those small statements, did you understand? Like when we remove one age, then what happens? Did you understand that? Tell me. Arpan, sir, planar graph not watched fully. Okay. So actually, in for this lecture, it is important that you watch the previous lecture. But anyway, first we will study age coloring. So you can study this. And if you have watched the planar graph video, if you have watched that, then you can study the planar graph also basically. But before everything, we will study age coloring. Okay, so let's start with age coloring first. Okay, so let's see. We have already seen the chromatic number, right? Chromatic number means vertex coloring. Chromatic number. What is chromatic number? This is the minimum number of colors needed to vertex color a graph. Okay, so this is called chromatic number. Now, in this chromatic number, so can anyone tell me one statement we have seen? One statement we have seen that for any graph, okay, any graph G you take, for any graph G, what we know? We know that this chromatic number is less than equal to the maximum degree plus 1. This statement we have seen. For any graph, this will happen. Okay, for every graph, this will happen that the chromatic number is less than equal to maximum degree plus 1. This is the maximum degree of the graph. This is the maximum degree of graph. Okay, so this is the maximum degree of graph. Now tell me, so this statement we know, we have already seen this statement. Can anyone give me one example where this will become exactly equal? Where this will become exactly equal? Can anyone tell me? Okay, can anyone give me a graph for which this will become exactly equal? We know that for every graph, you know that for every graph, whatever graph you take, for every graph, what will happen? For every graph, this will happen. That the chromatic number is less than equal to delta plus 1, where delta is the maximum degree of the graph. So tell me, anyone want to give me a graph? Okay, so give graph. This is the question basically. Give graph for which? Give graph. Okay, for which delta of this chromatic number is exactly equal to delta plus 1. This is exactly equal to delta plus 1. So which graph you will give me? Okay, so yes, the first graph that you can give me is odd cycle. Odd cycle you can give me, right? Yes or no? The first graph you can give me is odd cycle. Odd cycle. This odd cycle you can give me. In this odd cycle, what will happen? Like this is an odd cycle. This is an odd cycle. This is an odd cycle. Like C3, C5. So tell me, what is the maximum degree in this odd cycle? What is the maximum degree in odd cycle? What is the maximum degree? Maximum degree is 2. Correct? Maximum degree is 2. But what is the chromatic number of the odd cycle? What is the chromatic number of the odd cycle? That is 3. Okay. So you can clearly see that chromatic number is equal to 2 plus 1. Okay. Chromatic number. So this is the idea. Chromatic number of odd cycle. Chromatic number of odd cycle. That is maximum degree plus 1. Okay. And maximum degree is 2. This maximum degree, this is your 2. Okay. So this one graph you can give me. Another graph, what you can give? Another graph you can give is complete graph. Kn you can give. In this Kn, first of all, tell me what is the chromatic number for this Kn. What is the chromatic number of Kn? The chromatic number, every vertex should get different color. Every vertex should get different color. And what is the maximum degree in this Kn? What is the maximum degree? Every vertex has degree n-1 because every vertex has n-1 adjacent vertices. Okay, so every vertex has n-1 edges. So very simple. So every vertex has degree n-1. Again, you can notice that this will happen. Now, let me tell you one very interesting thing. One very interesting thing. Is there any other graph? Is there any other graph for which this will happen? Is there any other graph for which this will happen? Is there any other graph? Let me tell you, there is no other graph. Okay. So there is no other graph. There is no other graph. There is no other graph for which chromatic number will be equal to delta plus 1. Okay, there is no other graph. Only these graphs are there. There is no other graph where chromatic number is. What is the chromatic number of Qn? Like someone is saying, Saurav is saying Qn. What is the chromatic number of Qn? Tell me, what is the chromatic number of Qn? Chromatic number, Qn is a bipartite graph. Qn is a bipartite graph. In the last class, we have already seen the chromatic number of Qn, that is 2 for n greater than equal to 1. That is 2 for n greater than equal to 1, and that is 1 for n equal to 0. Okay, so that we have already seen. So you can notice this is interesting, right? This is interesting that these are the only graphs. These are the only graph. This odd cycle and this complete graph. These are the only graphs where delta is equal to the chromatic number is equal to maximum degree plus 1. No other graph for which, okay, this is known as Brooks theorem. This is proven by Brooke. Okay, so this is known as Brooks theorem. What he says that all the connected graphs, if you take, actually this will work for every graph. Okay, this will work for every graph, connected, disconnected, this will work for every graph. So anyway, but mostly we are interested in the connected graph. So all connected graph have this chromatic number is less than equal to maximum degree. Okay, this chromatic number is less than equal to maximum degree except Kn and odd cycle. So basically, this is the idea. Only these are there. Only these graphs which Kn, odd cycle. Only these graphs are there for which chromatic number is equal to maximum degree plus 1. And for all other graphs, for all remaining graphs, for all other graphs, remember, for all other graphs, what will be the chromatic number? The chromatic number is less than equal to delta. The chromatic number is less than equal to delta. Okay. Only these graphs we have where chromatic number is delta plus 1. Only these two graphs, complete graph and odd cycle. Only these two graphs we have where chromatic number is less than equal to equal to delta plus 1. Okay, and this statement, this Brooks theorem will actually, this is actually applicable for all the graphs. This is actually applicable for all the graphs. Okay, Why this is applicable for all the graphs? See, if you have a disconnected graph, then also this is applicable. If your graph is disconnected, let's assume you have a disconnected graph, okay, with maximum degree delta. Let us assume your maximum degree is delta. Then because you have disconnected graph, so there is a component here. Let me call it a component maybe. Okay, so this is your component C, component 1, and this is some component 2. Okay, this is some component 2. Now you can notice, and so on, there can be components. So the maximum degree is delta. Tell me one thing. The colors that you are using here, can you use those colors here? Right? Yes. Because there is no edge. Very simple. Okay, there is no edge. Like, for example, just think about it. Okay, like if I ask you, this is your question. Consider this graph. Like, okay, you have this graph, this, and your graph is like this. Your graph is this. This is your graph. Okay, and let's assume these are the vertices. So this is your graph G. Let us assume this is your graph G. This is the graph G. Then what is the chromatic number of graph G? What is the chromatic number of this graph G? So for this graph G, you can notice one thing. You can notice that all the colors that you have, all the colors that you use here, those you can use again. For example, if I use, let's assume, if I use red color here, okay, green color here, black color here, because this is an odd cycle. Now this red color I can use again here, no problem, because there is no edge, there is no problem. I can use red color here, black color here, green color here, yellow color here. Again I can use red color here, black color here, red color here, black color here. Again I can use red color here, red color here. So ultimately the chromatic number is basically equal to, okay, the chromatic number is actually equal to 4. The chromatic number is actually equal to what? 4, yes or no? Because your graph is like this. So the chromatic number will be this. Can I say this very interesting note? Can I say that if you have, let's assume you have a graph with k components. Let's assume you have a graph with k components. There are k components. Okay, k components. If you have a graph with k components, then what can you say about the chromatic number of this graph? The chromatic number of this graph, that will be equal to the maximum among, okay, chromatic number of each component. Yes or no? Yes or no? The maximum of, you take maximum of chromatic number of each component. Like, see, this is your graph. Total how many components you have? Total 5 components you have. Then the chromatic number of this graph, this will be the chromatic number of this graph. Very simple. Because these are the, this component is using maximum number of colors. This component, this is using maximum number of colors. Okay, this is using the maximum number of colors. All other, they are not using as much as color as this. This is using maximum number of colors. So I can say that chromatic number of this whole, this graph, that is the maximum among all the chromatic number of all components. Maximum of all components. Chromatic of all components. Okay. So just take max of chromatic number of components. Very simple, isn't it? Just take maximum of chromatic number of all components. Just take the maximum. Okay, that will be your idea. So for example, here I can say, so this will be actually the maximum of, 3, 4, 2, 1, 1. Okay, and that will be 4. This is what you have to take. So anyway, this Brooks theorem, this is actually applicable because if you have a disconnected graph, let's assume, and maximum degree is delta, then the chromatic number of this will be what? If the maximum degree is delta, then the chromatic number of this will be less than delta plus 1. The chromatic number of this will be less than delta plus 1, and so on. And ultimately the chromatic number will be what? Ultimately, what will be the chromatic number? Ultimately, the chromatic number, again, that will be less than delta plus 1. Again, that will be less than delta plus 1. Yes or no? Very simple. Because this is your component. So this component will have less than delta plus 1. This component will have less than delta plus 1. So every component has less than delta plus 1. So ultimately this whole graph, this will also have less than delta plus 1. Okay. So this is the idea. So I can say this will actually work for all the graphs. So you can remove this from here. This will work for all the graphs. All graphs have chromatic number less than equal to delta G except Kn and odd cycle. Okay, except some component, like, okay, some component is Kn or odd cycle. So actually this is the idea. So all disconnected, let me just write it here. So let me write it here. All graphs, remember, all graphs, disconnected, connected, all graphs have chromatic number less than equal to delta plus 1. This is your first statement. This is your first statement. This you already know. And the second statement is all graphs have chromatic number less than equal to delta if and only if. What should I write? Less than equal to delta if and only if no component, if and only if no component, if and only if no component is K, no component is complete graph or odd cycle. No component is complete graph or odd cycle. Or odd cycle. Okay. Is this clear? Okay. So all graphs have, yes, this statement is correct. All graphs have chromatic number less than equal to delta plus 1. This is fine. And all graphs have chromatic number less than equal to delta if and only if. I can say a graph has, I can say every graph, a graph has chromatic number less than equal to delta if and only if no component is complete graph or odd cycle. Actually, here it will not be like this. Sorry for that. This statement is actually not correct. Okay, so because this statement is actually not correct. The reason is because the maximum degree that can be like, okay, this statement is actually not correct. The reason is this. Consider this graph. Now, in this graph, you have an odd cycle. Okay, but the maximum degree you can take like this. This graph you can take. Okay, so this is your graph G. Then tell me what is the chromatic number of G? What is the chromatic number of G? Chromatic number of G, that will be, okay, so chromatic number of G actually will be 3. But what is the maximum? But what is the maximum degree? But what is the maximum degree of G? The maximum degree of G, that is 3. So that is actually 8. The maximum degree is actually 8. Okay, so this statement, okay, so this statement is actually wrong. Okay, because you can notice this statement is wrong. So anyway, you got the idea. Basically, the complete graph and odd cycle. This is what you have to take care. Okay, because you have odd cycle, but the maximum degree can be from other component, right? The maximum degree can come from other component. Yes or no? Are you getting my point? See, this is odd cycle, but the maximum degree, the maximum degree that can come from other component. Okay, so the maximum degree can come from other component. This is your maximum degree vertex. So the maximum degree can come from other. Okay, so anyway, let's move on, because so finally actually you can understand this, that you have to take care of Kn and odd cycle. This is what you have to take care. Okay, so this is the idea, but this is correct. If your maximum degree is delta, you have a graph G, disconnected graph G, which has maximum degree delta, then it automatically means that every component has chromatic number less than equal to delta plus 1. So the chromatic number of this graph, that will be less than equal to delta plus 1. Okay, so this is what you have to take. Okay, right. So remember, this maximum degree can come from other vertex. This maximum degree, this can actually come from some other vertex. This is not coming from C3. You can notice this maximum degree vertex. This is not coming from C3. this is coming from some other vertex, it can come. Okay, anyway, so this is the idea. So Brooks theorem is important because that tells you that only this complete graph and cycle graph, or sorry, odd cycle, complete graph and odd cycle, only these are the graphs where chromatic number is equal to maximum degree plus 1. For all other graph, for every other graph, the chromatic number, okay, and we are talking about connected graph, we are only talking about connected graph. For all other connected graph, the chromatic number will be less than equal to delta. Okay, so that is the idea. This is your Brooks theorem. Okay, so we are talking about connected graphs. Let's move on now. So next is edge coloring. What is this edge coloring? Very simple. Give the neighbor edges different colors. The same concept. Neighbor edges must get different colors. Like for example, let's assume that this is your graph. Okay, let's assume this is your graph. Tell me which edges, like these are your edges, E1, E2, E3, E4. Which are adjacent? Which edges are neighbor edges? Which are neighbor or adjacent edges? When they share a common endpoint, right? Okay, adjacent edges means sharing common endpoint. Sharing common endpoint. Sharing a common endpoint. Common endpoint. So you can notice that this E1, E3, these are adjacent. These are adjacent. E1, E4, they are not adjacent. So you can notice E1, E3, they are sharing a common endpoint, right? They are sharing a common endpoint. Very simple. So these are adjacent. Now let's color them. Now edge coloring means neighbor edges should get different colors. Neighbor edges, they should get different colors. Now what? See, if I give this color to this edge, if I give this color to this edge, then can I give this same color here? Can I give this same color here? No, because these are adjacent edges. So I have to give different color here. Okay, I have to give different color here. Can I give this same color? Can I give here? No, because adjacent edges should get different color. Can I reuse? Yes, I can reuse this color. I can reuse this color, and here I can reuse this color. So this is the idea. Minimum how many colors you need? Tell me minimum how many colors you need. This is your edge chromatic number. What is edge chromatic number? Edge chromatic number, that is, okay, remember edge chromatic number, that is minimum number of colors. So edge chromatic number is represented like this. Okay, zeta dash. So zeta dash is 2. Okay, zeta dash is 2 for this graph. So this is the idea of edge chromatic number. Very simple concept. Let's see what is the, if I have this graph. If I have this graph, consider this graph. For this graph, what is the zeta and what is zeta dash? A, B, C, D, E, F, G, H. So you find out zeta also for this graph. This is your star graph. And you find zeta dash also. Edge chromatic number and chromatic number. So what that will be? Give me a second. Yes. So what is the chromatic number here? The chromatic number is very simple. See, you can give one color here, and all these you can give same color, like white color here, and they can be given red color. Okay, so the chromatic number is actually 2. The chromatic number is 2, but what is edge chromatic number? Edge chromatic number will be equal to here you can notice that we cannot use any color. Okay, we cannot use any color, so that will be 7. See, if I give, just think about it. So that will be edge chromatic number. It will be like this. So this will be 2 and this will be 7. Because if I give this color here, I cannot give this color again. I cannot give this color again. I cannot give this color again. So I can give this color here. I can give some other color here. I can give some other color here. Okay, I can give some other color here. So like this, some other colors I am using. Okay, so this is the idea. Okay, yes or no? So the age chromatic number will be actually 7 here in this graph, because in this graph what is happening, you cannot use the color because all the edges are adjacent. Actually in this graph, can you notice all edges adjacent? All edges are adjacent. This is like, okay, all the edges are adjacent in this graph. All edges adjacent. Okay, so this is the idea. What is the chromatic number of this graph? So remember edge coloring. You know, edge coloring means don't give same color to adjacent edges. So that is the idea of edge coloring. So tell me, what is the edge coloring number of this graph? What is the edge coloring number? Zeta of this graph. Zeta dash of this graph. So for this graph, you can notice one thing. What is the maximum degree vertex? Can anyone tell me? This vertex is maximum degree. Tell me, what is the degree of this vertex? The degree of this vertex is actually 4. So can I say that at least 4? Can I say at least 4 colors you need? Because see, one thing you notice, if I give this red color here, I cannot use this red color here. I have to give this color here, and I have to use some other color here, and I have to use some other color here. So can you notice that because of this vertex, at least I can guarantee that I need at least 4 colors, because this vertex has degree 4. This vertex has degree 4. So it means all these 4 edges are adjacent. All these 4 edges are adjacent. These 4 edges, they are adjacent. So they should get different colors. Now, can you reuse the color? So definitely this should be, definitely I can say that this should be greater than equal to 4. Definitely. Okay, because this vertex has degree 4. So these 4 edges are adjacent. So these 4 edges should get different colors. Now, can I reuse a color? Yes. For example, this color I can reuse here. This color I can reuse here. This color I can again reuse here. Okay. Next, this blue color I can reuse here. This blue color I can reuse here. And this blue color I can again reuse here. Okay. So that is the reason I can say that the chromatic number, this age chromatic number will be 4. Is this clear? Age chromatic number, this is 4. Okay. Is this idea clear? So this, remember this age chromatic number, age chromatic number, age chromatic number. Another name is chromatic index. The another name is chromatic index, not chromatic number, chromatic index. So if they ask you chromatic index, then they are asking age chromatic number. Remember this part. Okay, so the another name is chromatic index, and the symbol is zeta dash. This is the symbol. And what is chromatic number? If I ask you directly, if I directly ask you what is chromatic number, then that means vertex chromatic number. Then that simply means vertex chromatic number. I told you by default chromatic number means vertex chromatic number, and that is your zeta of G. So remember, this is chromatic index. Okay. So very simple. So like this. Now let's see one result. This result, and this is very simple result, that for any graph, what I can say, what is the relation between maximum degree and age chromatic number? For any graph, the age chromatic number, that will be what? That will be greater than equal to maximum degree. Yes or no? That will be greater than equal to maximum degree. And the proof is very simple, because, okay, this is the proof. So let's assume vertex V has, degree, this, okay, degree delta, maximum degree delta. Vertex V has maximum degree, okay, and that is your delta. Then in this situation, this vertex V, okay, so these are the delta edges. Okay, these are the delta edges. There can be other vertices. You can have other vertices, you can have other edges. Okay, so but this idea, So, okay, you can notice these, all these delta edges, they are adjacent. All these delta edges, okay, all these delta edges are adjacent. Edges are adjacent. And because all these delta edges are adjacent, so I can say that they should get different colors. So I can say edge chromatic number will be definitely greater than equal to delta. Okay, is this clear? Very simple proof, very simple. Because, and same thing you can see in the star graph. In the star graph also you can see the same thing. Like this is your star graph K1, 4. This is the star graph A, B, C, D, E. In this graph you can notice this has maximum degree, that is your 4. This has degree 1. Every vertex has degree 1, but this vertex has degree 4. And you can notice because this vertex has degree 4, so for this graph, the edge chromatic number will be 4 for this graph. Okay, let's see. So that is the idea. Okay, so all the things we have seen. Now one very important theorem. This is extremely important theorem, because this theorem is actually very nice. Okay, like it will become one of your favorite, and the reason I will tell you. Because what this theorem says, this theorem basically says that, okay, so this theorem is for edge chromatic number. Remember, this is for edge coloring, and this theorem is very this theorem actually makes our work very easy. Vizing theorem. Okay, for edge coloring. This is for edge coloring. Remember, this is only for edge coloring. And this theorem, what this theorem says, this theorem makes our work very easy. This says that this edge chromatic number, this is always equal to either delta or delta plus 1. This is equal to delta or delta plus 1. Very simple. See, isn't it? Like our work is very easy now. Only two things we have to check, either delta or delta plus 1. So the edge chromatic number will be either delta or delta plus 1 for any graph, This we already know. This is very simple. See, this we already know that, you know that for every graph, this you already know, for every graph, whatever graph you take, this is very simple to understand. For every graph, you know that edge chromatic number that is greater than equal to delta, this we already know. This is simple. The proof we know. This is simple. Okay, simple fact. Okay, this should happen for every graph. This should happen for every graph. Whatever graph you take, this should happen. This we have already seen. And what Vizing says, Vizing says that yes, that is fine. Yes, that is fine. This will happen. That is fine. But the maximum can be delta plus 1. For every graph. So either delta or delta plus 1. This is the idea. Now let's find out the graph where you have delta plus 1. Okay, now it is very interesting that every graph, you can divide the graphs into two categories. Okay, yes or no? You can divide the graphs into two categories. You can divide these two categories. You can create, you can call them class 1 graph and you can call them class 2 graph. Okay, class 1 graph are where edge chromatic is equal to delta, and class 2 graph are where edge chromatic number is what? Where edge class 1, class 2. Class 1 means chromatic index delta. Class 2 means chromatic index delta plus 1. Now what we have to find out? We have to find out which is class 1, which is class 2. And this is not easy. Okay, one thing, this is not easy. Which is class 1, which is class 2, this is not easy. But let's see the standard graphs. Okay, all the standard graphs, let's find out, okay, where they belong. So what do you think where Cn belongs? Where Cn belongs? Class 1 or class 2? What do you think? Check it. Where it will belong. So first let's see C even cycle. Even cycle, like for example, this is a even cycle. This is a even cycle. So where they belong? Which class? Class 1 or class 2? See, very simple. Here you need how many? Okay, chromatic index. Here chromatic index will be 2. Okay, if I give color number 1, color number 1 here, color number 2, color number 2 here. So this is chromatic index. Okay, here also chromatic index is 2. Here also chromatic index is 2. Color 1, color 2, color 1, color 2, color 1, color 2. Okay, so for C even, this C even, this is in which class? This is in which class? Class number 1. This is in class number 1 because the maximum degree is also 2. The maximum degree is also 2. And what about odd cycle? What about odd cycle? What about odd cycle? So odd cycle. So the delta, delta is 2. But what is the chromatic index? The chromatic index is 3. If I give color number 1 here, now I have to give color number 2 here. I cannot use color number 1, color number 2, so I have to give color number 3 here. Similarly, color number 1, color number 2, color number 1, color number 2, now color number 3. Okay, so chromatic index is actually 3. So you can notice that chromatic index, that is equal to delta plus 1. That is equal to delta plus 1. Okay, so this is your class 2. I can say. Is this clear? Cn. Okay, similarly, what about Pn? What about Pn? Pn, every Pn is class 1. Every Pn is class 1. Why? Because the chromatic index will be 2 and that is equal to delta. Okay. Here, remember, it should happen that n should be greater than equal to 2. You must have at least 2 vertices. So this Vizing theorem, this says that actually this will work. Even if n equal to 1, then what will happen? Even for this vertex also this will work. See, even for P1 also this will work. Because here, what is the maximum degree? The maximum degree is 0. And what is the age chromatic number? Age chromatic number. What is the age chromatic number here? Age chromatic number, that is 0. And what is the chromatic number here? What is the chromatic number? The chromatic number is 1. So if you want to color the vertex coloring number will be 1. But age coloring number, that will be 0. Okay, so this will work always. This Vizing theorem will work always. So this is the idea. So every Pn, if you have any Pn you take, like this is your Pn, then you can notice that the maximum degree is 2 and you can give this color 1, 2, 1, 2. Okay, so here age chromatic number also will be 2. So this is your class 1 graphs. Okay, like this you can see. And what about Kn? What do you think about Kn? Like we already know this is your class 2. We already know this is class 2. This is class 2. This we already know. What about this one? What about this one? What about this graph? So here, what I can do, you can clearly notice that we need color number 1, color number 2, color number 3. At least 3 colors we need. Okay. At least 3 colors we need. Now, can I use color number 1 here, color number 2 here? Yes. And I can use color number 3 here. So for this, actually, this is your class 1. This is your class 1 because the chromatic index, that is equal to maximum degree. That is equal to maximum degree. So this is your class 1. So finally, what you can say? What you can say? K even means even number of vertices. If you have even number of vertices, K even is class 1. This is your class 1. And K odd is what? K odd is class 2. Okay, is this clear? So this is your K odd, that will be class 2. And K even, that will be class 1. Tell me, is it clear? And okay, so now let's see. This is your Vizing theorem. So Vizing theorem says that for any graph, age chromatic number will be either maximum degree or maximum degree plus 1. And this is a theorem by Koenig. He says that for bipartite graphs are class 1. Basically, this is the idea. Okay, this is the idea that bipartite graphs are class 1. All the bipartite graphs, okay, all the bipartite graphs are class 1. What it means? Class 1 means their chromatic index will be equal to their maximum degree. So all the bipartite graphs are class 1. All the bipartite graphs. And this is a statement by Koenig. Proof is not required. Proof is complicated. Okay, very complicated proof, but that we will not see. But the bipartite graphs are class 1. Very simple. All the bipartite graph. So tell me, this statement tells you how many graphs are class 1. Remember, all the bipartite graphs are class 1. So which graphs are bipartite? All the bipartite graphs are class 1. So which graphs are included? Like, okay, even cycle are included. Even cycles are included. Okay, so even cycles are included. Also, for example, Qn, hypercube graph, every tree, Pn. Okay, all these are what? Star graph. Yes, star graph, Km, N. All these are your class 1. All these are class 1. Class 1 means for them, the age chromatic number will be equal to their maximum degree. All these graphs are bipartite graphs. Okay, so this is the idea. All these graphs. So is this clear to everyone? All these points. So you can notice these are the definitions. Very simple. First, the definition of age coloring. Age coloring means to the edges we assign colors. To the edges we assign colors such that if two edges share a vertex, they should get different color. If two edges share a vertex, then they should get different colors. This is your age coloring. Next, what is chromatic index? Chromatic index means minimum number of colors that you need for age coloring. Okay, and this is Vizing theorem, that age chromatic number, that is always delta or delta plus 1. So basically two classes you will get. Okay, you will get basically two classes, class 1, class 2. Class 1 means, okay, where age chromatic number is delta, and class 2 means where age chromatic number is delta plus 1. And this is interesting, that which graphs are class 1, which graph is class 2, whether graph is class 1 or class 2. This is interesting. And for that, I told you that this is not easy. But this statement, okay, this is a standard statement. This can be shown actually. These things will help you. Let me tell you that this is not required for GATE exam, because in the GATE exam they will not ask you this. These statements they will not ask you, but actually there is a question in GATE exam. So those type of questions if come, then you can take the help of these things. What this is saying? This is saying that every class 2 graph must have at least 3 vertices of maximum degree. Remember, this is one-way statement. This is one-way statement. Means if you have a class 2 graph, class 2 graph means the age chromatic index is equal to delta plus 1. If you have class 2 graph, then what should happen? At least 3 vertices must have maximum degree. At least 3 vertices of maximum degree you must have. So at least 3 vertices must have maximum degree. At least 3 vertices with maximum degree. At least 3 vertices with maximum degree. But this is only one way. This is not this. So if you don't have at least 3 vertices of maximum degree, then definitely it is class 1. Okay, for example, if I create a graph, like for example, let me create a graph. Okay, let me create a graph. Now tell me, what do you think? What is the age chromatic number? So in this graph, you can notice, just find out the degree. Degree is 2. What is the age chromatic number? Age chromatic number. So you can notice degree 2, degree 2, degree 1, degree 2, degree 3, and this is degree 4. This has degree 4, and this is degree 6. So this is class 1. This is class 1. Maximum degree is what? Maximum degree is 6. Here maximum degree is 6. But how many vertices are there? But you can notice that, okay, less than, you can notice less than 3 vertices. You can notice less than 3 vertices of maximum degree. Less than 3 vertices of maximum degree implies class 1, implies not class 2. Okay, implies not class 2. So it means chromatic number will be equal to maximum degree. So the answer will be 6. You don't have to check it. You don't have to check it. This will be class 1. Is this clear? Is this clear? That every class 2 graph, that is basically, that will have at least 3 vertices of maximum degree. It means if you have less than 3 vertices, if you have less than 3 vertices of maximum degree, okay, then it simply implies that this is class 1. Again, this is one-way statement. This is not correct. Again, this is one-way statement. Why this is one-way statement? This statement is one way because you can take, for example, consider class 1 graph. Like this is your class 1 graph. We already know. This is your class 1 graph. Here, every vertex has degree 2, 2, 2. So actually there are more than 3 vertices. You can notice there are greater than equal to 3 vertices of maximum degree. And your maximum degree is actually 2. But still this is what? But still this is class 1. Okay, so this statement is one way. Means if your graph is class 2, then you must have at least 3 vertices of maximum degree. This is just a one-way statement. There is no name for this property. This is actually proven by Vizing. Again, Vizing proved it. This is a part of Vizing theorem. And this is one more standard. This is very standard actually, because all the books that I studied on this edge coloring, for this edge coloring, I studied many books, and I found one common thing I found, that this is what they talk about. See, finding class 1 or class 2 is not easy. Let me tell you. Okay, finding class 1, class 2. Okay, finding if G is class 1 or class 2. If G is class 1 or class 2 is not easy. Remember, is not easy. This is actually NP hard problem. Let me tell you again. This is your NP hard problem. This is actually NP hard problem. Okay. So if for the GATE exam, what we will do? We will check manually. Okay. Like either we will apply the things that I'm telling you. Okay. For GATE. Okay. Either check manually. Okay. Either check manually or use facts I told. Facts we save. Okay. So this is the idea. If facts are not applicable, if facts are not applicable, because all these facts are basically one way. So if facts are not applicable, then you do manually. This is the idea. And this is just one last thing I want to tell, that every regular graph with odd number of vertices is class 2. Every regular graph with odd number of vertices is class 2. So means regular graph with odd number of vertices, that is class 2. Which are regular graphs? Can anyone give me some examples? Regular graphs with odd number of vertices. Regular graphs with odd number of vertices, which are class 2, like cycle graphs, C odd, like C odd, like K odd. Yes or no? C odd, K odd. Okay. So these are your class 2. And we have already seen these are class 2. Okay. Again, this statement is one way. So regular graphs on odd number of vertices, these are class 2. But okay, so this is like you have a regular graph, regular with odd number of vertices, that implies class 2. But remember, this is not correct. Okay, this is not correct. So regular graph with odd number of vertices, that will be class 2, but this is not correct. So again, only one way statement. So if you see any regular graph, with odd number of vertices, then it will be class 2. Okay, is this clear? Can anyone give me a counter example here? I think like counterexample will not be easy, but anyway, this is one-way statement. Okay, and for bipartite graph, Nikhil is saying KML. No, counterexample means it must be, see, bipartite graph are class 1. Nikhil, we have already seen. Bipartite graphs are class 1. Bipartite graph, those are class 1. Okay, anyway, so don't worry about it. These things are not required for GATE exam. I don't think they will ask. Okay, so I don't think, so don't worry about it. So anyway, you can notice this is a bipartite graph, and bipartite graph is class 1. So for this graph, tell me what is the chromatic index? What is the chromatic index? Chromatic index will be, this is class 1, so delta, and that will be 4. You don't even have to check it. Are maximum degree, Kusal, maximum degree is 4. This is a bipartite graph. Why this is bipartite graph? There is no odd cycle. There is no odd cycle. There is no odd cycle. You can notice there is no odd cycle. So this is a bipartite graph. There is no odd cycle. And for bipartite graph, this is class 1. Every bipartite graph is class 1. You know, every bipartite graph is class 1. So that will be equal to 4. And what is the chromatic number? What is the chromatic number for bipartite graph? That is 2. Chromatic number will be 2. Is this clear? Let's see this GATE exam question. This is latest GATE 2020. What should be the answer for this question? So the question is asking that a graph is obtained by adding a vertex S to K34 and making S adjacent to every vertex of K34. The minimum number of colors required for edge coloring. Basically, the question is asking chromatic index. The chromatic index. The question is asking chromatic index. This is the question on chromatic index. And this is your latest GATE exam question. So tell me what should be the answer. Just think about it. So the question is saying that this is K34. You have K34. Like this is your K34. Let's assume A, B, C. Okay. And 1, 2, 3, 4. Or maybe X, Y, Z, W. And what you are doing to this K34, this is a complete, remember, K34 means complete bipartite graph. This is your complete bipartite graph. Now you are adding a vertex S and you are making it adjacent to every vertex. This vertex S you are adding and you are making it adjacent. You are making it adjacent to everyone. You are making it adjacent to everyone. You are making it adjacent to everyone. Tell me one thing you tell me, for this vertex, because of this vertex, what is the degree of this vertex? What is the degree of this vertex? That will be 7. And you know, okay, so for this graph, what is the maximum degree? Now, this is your graph G. For this graph, what is the maximum degree? Like this vertex will have, what is the degree of this vertex? Tell me what is the degree of A? Degree of A is 5. Degree of B is also 5. Degree of C is also 5. Okay, degree of this is 4. Degree of this is 4. Yes or no? This is degree 4, this is degree 4. So the maximum degree is actually 7. So the answer should be what? The answer should be what? Either 7 or 8. The answer should be 7 or 8. Yes or no? The answer should be 7 or 8, correct? Answer should be 7 or 8. So what should be the answer? Answer should be 7 or 8. So what should be the answer? So the answer will be actually 7. Why? What is the reason? See the reason. Let me tell you the reason. Why the answer will be 7? Because you can notice that these edges will get different colors. All these, they will get different colors. Okay. So these will get different colors. And then finally, what we need to color? We need to color these edges. We need to color these edges. Okay. And you can see actually, less than 3 vertices of, yes. Oh, right. Nice, Nikhil. Because actually this, if you notice, if you try to prove it, then that will be complicated. If you try to prove it, then that will be actually complicated, because you cannot use these colors. You cannot use these colors, but using these colors, how will we color these vertices? There will be remaining how many edges are there? Tell me, remaining how many edges are there? Remaining total 12 edges are there. Remaining how many edges are there? Remaining how many edges are there? Total 12 edges are there remaining. Okay, so what we will have to do? We will have to check remaining 12 edges are there. Yes or no, Akash? This is a K34. This is your K34. K34 plus a vertex S. So remaining 12 edges are there. So the okay, you can notice the maximum degree is 7. So the answer will be either 7 or 8. But you know that, okay, less than 3 vertices. But you know that less than 3 vertices of maximum degree. So class 1. So class 1, and hence the answer will be 7. So the answer will be 7. Okay. So like this you can do, and the answer will be 7. So all these things that we have seen, that facts you can use and you can solve this question. Okay. Actually, this question is not easy. Let me tell you, this question is not easy, but because see, you need 7 colors, that is fine. But the answer can be 7 or 8. You know, maximum degree is 7 for this graph. For this graph, maximum degree is 7. Okay, so answer will be 7 or 8. But how to find out whether 7 or 8? So this thing is actually not easy. If you read all the answers on GATEOverflow, then those answers are also vague, I can say. Okay, like all those answers are basically either they are manually doing. Okay, so that will be complicated. So you can just use this fact that there are less than 3 vertices of maximum degree. So that's the reason answer will be 7. So this is class 1 graph. Okay. So very simple. Let's see this example. Tell me what is the chromatic number. Find chromatic number for these graphs. Okay. So tell me the chromatic number of these graphs. Let's find out what is the chromatic number of this graph. For this graph, this is your K4. This is your K4. You know, this is your this is your W4. Field graph on 4 vertices. So what is the chromatic number for this? This color I cannot use. Okay, this color. So if I give this red color here, I cannot use this red color here. And for the outside, okay, if I give this red color here, I cannot reuse this red color here. Vertex coloring I am asking. I am asking vertex coloring. Okay, so for the outer vertices, you need 2 colors. So the answer will be 3. For this, this is your wheel graph. What should be the chromatic number of this? Do we have odd cycle? There is no odd cycle, right? There is no odd cycle. So what we have to do? Here we don't have any odd cycle. We don't have 5 length cycle also. 3, 4, 5, 6, 7, 8. We don't have odd cycle. In this graph, we don't have odd cycle. So let's do manually. So if I give, for example, if I give color number 1 here, then I have color number 1, then I can reuse color number 1 here, and I can give color number 2 here, reuse color number 1, color number 2, reuse color number 1, and here I can use color number 2, and here, okay. So the answer will be 2. Very simple. This question is actually very simple. So the chromatic number will be 2 for this graph. I'm asking chromatic number, means vertex chromatic number, vertex coloring. What is the answer for this graph? Is this complete graph? Is this complete graph? This is not complete subgraph. Okay, this is not complete subgraph. So take care. So here we have a triangle. So I can directly give 3 vertices. I can directly give 3 colors. Directly I can give 3 colors. Now I can reuse color number 2 here. I can reuse color number 2. I can reuse color number 1 here. Okay, now this is very simple. Color number 1, color number 2, color number 1, color number 2, color number 1. Okay, color number 2, color number 1, color number 1, and color number 2. Okay, so now, so for this graph, the chromatic number will be 3. Okay, let's find out the age chromatic number. Let's find out what is the age chromatic number. What that will be? Age chromatic number. Again, class 1 or class 2. This is very simple. Age chromatic number is actually simple also, hard also. but this is actually for us, this is very simple. Class 1, class 2. So we have to find out which is class 1. Okay, which of them is class 1? So what do you think? Which is class 1? Is this class 1? Here, how many vertices of maximum degree? How many vertices of maximum degree? How many vertices of maximum degree? This at degree 3, this at degree 3, this at degree 3. You can notice this at degree 3 and this at degree 3, this at degree 4. So this is your class 1, right? This is your class 1. This is the class 1 because only for this graph I can say less than 3 vertices of maximum degree. Less than 3 vertices of maximum degree. So this is class 1. So this graph is actually class 1. So the chromatic number will be equal to delta. The chromatic number will be equal to delta. Chromatic index will be 4. For this graph, chromatic index will be 4. What about this graph? What about this graph? In this graph, what happens? So here you have many. Okay, so here you cannot apply this concept. You cannot apply here. In this you cannot apply this concept because here we have many vertices of degree 3. The maximum degree is 3, right? The maximum degree is 3, and this side degree 3, this side degree 3, this side degree 3, this side degree 3. So this is one way. You cannot say class 2. Don't say class 2. Okay, don't say class 2. So what should I do? So I should do manually. Okay, don't say class 2. I have to do bipartite. Yeah, right. Oh, right, very good. So yes, this is bipartite. Because there is no order cycle, so this is bipartite. And because this is bipartite, so this is class 1. Again, this is your class 1. So here chromatic number will be equal to 3. Chromatic index will be equal to 3. Because this is bipartite. This graph is bipartite because there is no odd cycle. There is no odd cycle. So this is bipartite. So I can say chromatic index will be equal to 3. Class 1. And what about this graph? What about this graph? This graph is not bipartite. First of all, this graph is not bipartite. What about the maximum degree? The maximum degree here, this vertex has degree 5. And no other vertex has degree 5. This vertex has degree 5. No vertex has degree 5. So delta is equal to 5. So this is also class 1. This graph is also class 1. So the chromatic index will be 5. For this graph also you can say this statement. Okay, like this. Is this clear to everyone? Tell me. So this is what you can do to find chromatic index. This is what you can do to find chromatic index. To find chromatic index, this is what you can do. First you remember that chromatic index will be delta or delta plus 1. This is the first thing you remember. Chromatic index will be delta or delta plus 1. The second thing what you will check. If less than 3 vertices of maximum degree. If less than 3 vertices of maximum degree. If less than 3 vertices of maximum degree, then class 1. Okay, then class 1. Then class 1 means, okay, zeta will be equal to delta. Then class 1. What is the next statement? If this is not working, I can say if this is not working, like, okay, if greater than or equal to 3 vertices of maximum degree, then what you do? Then check bipartite. Then check bipartite. Okay. If bipartite, then class 1. Okay. If bipartite, then class 1. And if not bipartite, then okay, then check manually. Then manually do. Okay. Then manually do. Also, one thing you can notice. Also, what you can notice? You can also notice that these things you can also notice. So 1, 2, 3, and this one also to find chromatic index. This is also these standard things you can remember. these standard things like regular graph with odd number of vertices. Regular graph with odd number of vertices, that will be what? Regular graph with odd number of vertices, that will be what? That will be class 2. Okay, regular graph with odd number of vertices, so that will be your class 2. Okay, so that's it. This is enough. Tell me, did you understand all about edge coloring, vertex coloring? We have covered everything. The GATE exam question. Can you notice that GATE exam question actually that is using this less than 3 vertices of maximum degree? That GATE exam question you can solve very easily. Like I can say maybe 10 seconds. You won't even take 10 seconds. Just check the maximum degree. Maximum degree is 7 and less than 3 vertices of maximum degree. That's it. So for that question, answer will be 7. Maybe 5 seconds, 10 seconds. Okay. Anyone has any doubt? Let me know. Do you have any doubt in the chromatic number, chromatic index? All these concepts we have seen. Now we will study planar graph. Actually, we have already studied planar graph in the last video. So if you have not watched the last video, then you can leave because we need the last video. Okay, you have to watch the last video before attending this. Okay, so you have to watch this video. The last video you have to watch before attending this planar graph. This is the second point, Nikhil. If less than 3 vertices of maximum degree, then class 1. Okay, let's move on now. So what is a planar graph? Those students who have watched the video, what is a planar graph? Planar graph means can be drawn in 2D without edge crossing. Okay, you can draw in 2D without edge crossing. Is this planar graph? Okay, so for example, is this planar graph A, B, C, D? Is this planar graph? This graph G, is it planar? Is G planar? Is this planar graph? Is this graph planar? Is this graph planar? Yes, very good. Very good. This is yes. Yes, this is planar. This graph is planar because I can create planar representation. I can create planar representation. You can notice I can create planar representation. So this graph G, remember this graph G, this is also planar graph. Yes, this is planar graph. Remember this is planar graph. Yes, no problem. This is planar graph. This is also planar. Both are same. Both graphs are same. This is also G. This is also G. So both are planar graph. But you can notice. This is planar representation. This is planar representation without edge crossing. Okay, so this is your planar representation. And this is not planar representation. This is not a planar representation, I can say. This is not planar representation. Not PR. Not planar representation. So this is very important. Planar graph means can be drawn in 2D without edge crossing. So like this is not a planar representation because there is a edge crossing here. These edges are crossing. So, okay, but you can notice that what I can do, I can draw it without edge crossing. So I can say is G planar? The answer is yes. So this graph is planar. This graph is planar. Okay. So this is important. Like this graph, is it planar? Is this graph planar? Yes, this graph is also planar. So remember this graph is planar. Why this graph is planar graph? This graph is planar graph because you can create a planar representation. This is your planar representation. This is not W3. Right. Yeah, yes. This is your K4 means W3. Okay. So tell me, we have edge crossing here. So can I say this is not planar? We have edge crossing. Edges are crossing. You can notice edges are crossing. So can I say this is not planar? This graph, can I say this is not planar? No, we cannot say. Actually, this is planar. This graph is also planar. So, okay, can I say not planar? The answer is no. The answer is no. This is actually planar graph. This is actually planar graph. Okay, because you can create without edge crossing. You can notice this graph, you can create without edge crossing. So this is your planar graph. And the next concept is region. Okay, the next concept is face. Tell me how many faces are there? in this graph, how many faces are there? How many faces? First you tell me, is this planar graph? First you tell me this point. Is this graph planar? Is this graph planar? First you tell me this point. Is this graph planar? The answer is yes. The answer is yes. Yes, this is planar graph. Now my question, how many faces are there in this graph? In this graph, how many faces are there? So remember, this concept of face, you already know. This concept of face, this is for planar graph. Remember, this concept of face is only for planar graph. This concept of face, this is only for planar graph. Okay, this concept is only for planar graph. And also remember, if you want to find face, then you find in the planar representation. So faces are found, remember, faces are found in planar representation. In planar representation. So you must have a planar representation of a planar graph. Always remember faces. If you want to find how many faces are there, then can I say, is this correct answer? Like, can I say this is correct answer? That this is face number 1, face number 2, face number 3. Is this correct answer? Is this answer correct? Can I say number of faces is equal to number of faces means F, that is equal to 3? Is this correct answer? Okay, this is not a correct answer. This is not a correct answer because this is not planar representation. This is not a planar representation. So first you convert this into planar representation. This is very important. So what you will do? First you will convert this into planar representation and then you will find it. Okay, how to convert into planar representation? So like this you can convert. Okay, like this you can convert. What you can do? You can put this edge here and you can put this edge here. Okay, like this you can do. Now tell me how many faces are there? How many faces are there? Now you can notice this is one face. Face means any region which is surrounded by edges. So, okay, this is a face now. So this is your face number 1 and this is your face number 2. This is your face number 2. See, this is the face number 2. Is this clear? This is your face number 2. This is your face number 2, exterior, outer face, outer face. This is your outer face, infinite face. This is infinite face. And this is your interior face. So total how many faces are there? Number of faces is equal to 2. Now tell me what is the degree? Like if I say this is face 1, this is face 2, then what is the degree of face 1? What is the degree of face 1? Degree means, I told you, if you want to find degree, degree means how many edges it is touching. How many edges it is touching. So one edge, okay, one edge, I can say degree of face 1, that is 1 edge, 2 edge, 3 edge, 4 edge. So degree of face 1 is 4. And what is degree of face 2? Degree of face 2, that will be what? So degree of face 2 will be, okay, degree of face 2 will be like this. 1, okay, 1 edge, 2 edge, 3 edge, 4 edge. Okay, so degree of face 2 is also 4. So tell me what is total degree of faces? Total degree of faces. Total degree of faces, that will be 4 plus 4 is equal to 8. This should be equal to what? This should be equal to twice the number of edges. Twice the number of edges, and number of edges is 4. So you can notice. So this is the idea. Okay, very simple. So, okay, this is a planar graph because you can create a planar representation. Very simple. So you know what is a face in a planar graph. What is face? Face is basically area surrounded by edges. This is the idea. What is a face? You can very easily see the definition of face. What is the definition of face? Region of the plane bounded by edges. This is the definition of face. If I have any planar graph, okay, like for example, what about W3? What about wheel graph? Is it planar graph? Is a wheel graph planar graph? WN. Is this a planar graph? Can I say every WN is planar? Every WN. Yes, this is planar. Every WN is planar graph. Okay, every WN is planar graph. Why? Because very simple. Just think about it. Just think about it. You have CN. This is your CN. There is no edge crossing. This is your CN. This is your CN. There is no edge crossing, right? there is no edge crossing. And this is your middle vertex. This is your middle vertex. And again, there is no edge crossing. You can notice there is no edge crossing. We don't have any edge crossing. So every W1, that is a planar graph, every wheel graph. Now tell me, in this W4, how many are there? How many faces are there in this W4? So W4 means this is your W4. This is the W4. This is your W4. So in this W4, if you notice, face means area surrounded by edges. What is the definition of face? What is the definition of face? Face means area surrounded by edges. Area surrounded by edges. Surrounded by edges. Okay. So area surrounded by edges. Like this is area surrounded by edges. So I can say this is face 1. This is another area surrounded by edges. Phase 2. Area surrounded by edges. Phase 3. Area surrounded by edges. Phase 4. And this is another face. This is outer face. Outer face, phase 5. So total 5 faces you have. For interior, these are interior faces. These are limited faces. This is the limited area. But this is the infinite area. This is the infinite area. This outer face. So this is called infinite face. This is your infinite face. This is your infinite face, or you can call it exterior face. Because this is infinite. This is infinite. Okay. So this is the idea. And these are your interior face. This is an interior face. So this is the concept of face. What is the degree of F5? What is the degree of F5? So you can notice degree of F5 means this edge, how many edges it is touching? How many edges it is touching? So you can notice, okay, the answer will be 4. And what is degree of F3? What is degree of F3? How many edges it is touching? Okay, so that will be 3. Very simple. Okay, so this is the idea of face. And if you notice, in every edge, what is happening here? If you notice, because of every edge, what will happen because of every edge? If you have edge like A, B, if you have edge, this is your edge. You can think of this edge as you can think as a wall. This edge you can think as a wall. Now you can notice because of this edge, the total degree of face will increase by how much? Total degree of faces will increase by how much? Total degree of faces will increase by 2. Okay, by 2. The total degree of faces will increase by 2. So this is the idea. So total degree of faces increases by 2. Or I can say every edge contributes a value of 2 in the total degree of faces. You can notice every edge. If you take any edge, every edge contributes. Every edge contributes a value of 2 in the total degree of faces. Every edge will do this. Okay. Now let's analyze. So this is the analysis of WN. This is the analysis of WN wheel graph. For the wheel graph, you can very easily see. Okay. So this is the idea. Now, in a wheel graph in WN, how many faces will be there? Tell me, in WN, how many faces will be there? In WN, what is the number of faces in WN? What will be the number of faces in WN? So you can notice that there will be, like, first of all, there will be CN vertices. There are CN vertices. And for, okay, like this, you will get a face. And okay, so like this. So for every consecutive 2 vertices you take, you will get a face. Yes or no? So that will be actually n plus 1. What is the reason n plus 1? Because, see, you take any wheel graph you take. Like, for example, let me take this wheel graph. Like, let me take this W5. This is a W5. This is your C5. And in this C5, you can do this. So you can notice one thing, that how many faces will be there? Total 1, 2, 3, 4, 5, and outer face 6. So this is your W5, and there will be 6 faces. Okay. So in WN, number of faces will be n plus 1. Okay. One exterior This is one exterior and other interior faces. Okay, so this is a simple idea. What about tree? What about a tree? Can I say every tree is planar? Can we say every tree is planar? Yes, of course, every tree is planar. Every tree is a planar graph because there is no problem. Okay, every tree you can draw without edge crossing. Whatever tree you have, you can draw without edge crossing. For example, this is a tree. This is a tree, you can notice. Okay, so you can notice there is no edge crossing. Number of faces in a tree. In a tree, what will be the number of faces? How many faces will be there in a tree? There will be only one face. There will be only one face. There will be only one face in a tree. In a tree, you only have one face. Only exterior face. What is the degree of this? Like, okay, only one face you have, F. So what is the degree of this F? What is the degree of this F? Now you can notice that this F will touch this edge 2 times. This edge will touch 2 times. This edge will touch 2 times. This edge 2 times. This edge 2 times. This edge 2 times. This edge 2 times. This also 2 times. This also 2 times. So the degree of this will be actually every edge it is touching 2 times. So I can say 2 into n minus 1. 2 into n minus 1. Don't write like this. Don't write like this. This is wrong. This is wrong. Okay. So the answer will be 2 into n minus 1. So this is the idea. This is tree. Every tree is a planar graph. And the okay, only one face will be there and degree will be this. Okay, let's move on now. So you know the concept of face. Like here you can notice. But remember, if you want to find faces, then you have to find in the planar representation. Like, is this planar graph? This graph, is it planar graph? Yes, this is planar graph. This is a planar graph. Yes, this is a planar graph. But if you want to find number of faces, if I ask you what is the number of faces, then don't do like this. Don't do like this. First you create planar representation. Okay, so first you create planar representation and then you find number of faces. So number of faces will be 4. This is how you do. Okay, let's move on. The next thing is your this. So you can notice the total degree of faces, the summation of degree of all the faces. The total degree of faces is equal to twice the number of edges because every edge will contribute a value of 2. Every edge will contribute a value of 2 in the total degree of faces. Next is Euler formula. This is very important formula, let me tell you. You don't have to, like, the proof is not important, remember. For Euler formula, the proof is not important for the GATE exam. But the small facts are important. The small facts that I told you, those facts are important. What is this Euler formula? Euler formula is like this. If you have a graph G, if you have planar graph, this is only for planar graph. Remember, this Euler formula is only for planar graph. Only for planar graph. Your graph must be planar. Only for planar graphs. Your graph must be planar. Okay. So if this is the idea, if G is planar graph, if G is planar graph, this is a planar graph with the C components. With the C components, total number of components is C. With C components, then this will happen. What will happen? If G is a planar graph with C components, then this will happen that number of vertices plus number of faces, that will be number of edges plus number of components plus 1. Okay, is this clear? This is the Euler theorem. This is the Euler formula. And the proof we have seen. And in the proof, what is important, let me tell you. The proof is not important, but in the proof, what things are important. So let me tell you what things are important. First, you know what is the age. First, you note age which is part of cycle. Age which is part of cycle. Age which is a part of cycle. Part of a cycle. So what is age which is part of a cycle? Like for example, if I give you this graph, okay, let's assume that this is your graph. In this graph, you tell me which age is part of cycle. Okay, total, these are the edges. Like, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which edges are part of cycle? Tell me. For this graph G, which edges are part of cycle for this graph? You can notice 6 is not part of cycle, right? This 6 is not part of cycle. So I can say except 6. 6 is not part of cycle. This 6 is not a part of cycle. So except 6, 10, every edge is part of cycle. Yes or no? Except 6, 10, every edge is part of cycle. Now, when you remove edge which is part of cycle, then what happens? Tell me. You have a planar representation. Okay, you have a planar graph. This is the point what I want to say. So you have a planar graph. So, okay, notice. Okay, so this is important point. So let's assume you have a planar graph. You have a planar graph G. Let's assume you have a planar graph G. Your graph is planar. And then from this G, you remove one edge. You remove one edge which is part of cycle. Which is part of cycle. You remove one edge which is part of cycle. Then what will happen? Tell me what will happen. If you remove one edge, let's assume you have a planar graph. You have a planar graph with a number of vertices. Okay, number of vertices is greater than equal to 3. With the number of vertices is greater than equal to 3, number of vertices, then if you remove this type of edge, then what will happen? G minus, from this graph G, I am removing one edge which is part of cycle. Like for example, you can notice that this edge is part of cycle, like any edge you take. Okay, for example, if I remove this edge which is part of cycle, now at this moment, how many, okay, in this graph G, at this moment, how many faces? Number of faces in G. What is the number of faces in G at this moment? At this moment, 1, 2, 3. Okay, outer, 1, 2, 3. So 3 interior and 1 outer. So there are 4 faces in G. Now what I do? From this graph, I remove this S3. I remove this S3. Now, what is the number of faces? Now, what is the number of faces? Like I remove this I remove. This I remove. If I remove this, then what is the number of faces? If I remove this as a remove, then the number of faces will decrease. Now the number of faces is only 3. Okay, so this is the idea. You can remove any, that is your choice. Any edge which is part of cycle. So tell me which edge should I remove? Like here, at this moment, number of faces is equal to 4. If I remove any edge which is part of cycle, for example, if I remove this edge, for example, if I remove this edge, this is part of cycle. So if I remove this edge, then what will happen? G minus 8. Then what will happen to number of faces? Number of faces will decrease by 1. Because very simple, these two faces will become 1. At this moment, this face and this face, they are different at this moment. But if I remove this 8, this face and this face, they are different. But if I remove this edge, then these two faces will merge. They will merge. So this is what I'm saying. Okay. So if you remove from any graph, you have any planar graph with number of vertices at least 3. If you remove any edge, if you remove one edge which is part of cycle, then what will happen? Then number of faces will decrease by 1. Number of faces decrease by 1. Is this clear? One edge is gone, number of faces is decreasing by 1. If you remove this type of edge, decrease by 1. Number of faces will decrease by 1 if I remove one edge which is part of cycle. And another thing, if I remove one edge which is not part of cycle, then what will happen? If I remove one edge which is not a part of cycle, then what will happen? Which is not part of cycle, then number of faces will not decrease. Number of faces will remain same. Number of faces remain same. Okay. if I remove one edge which is not part of cycle, then number of components will decrease by 1. Number of components increase by 1. Number of components increase by 1. This will happen. Number of components will increase by exactly 1 if I remove one edge which is not part of cycle. For example, this is your graph. In this graph, if I remove 6, like here you can notice that number of faces is equal to 4. Number of faces equal to 4, original graph for this graph G. And number of components, how many? Number of components is 1. Now let me remove this G minus 6. Let me do G minus 6 because, okay, so this edge I am removing. If I remove this edge, then what will happen? For this, the number of faces, what is the number of faces? The number of faces is still 4. Number of faces is still 4, but the number of components that has increased by 1. That is increasing by 1. The same thing you can do. The same thing you can do if you remove this edge. Like, okay, instead of this edge, if I remove 10, if I remove this edge 10, this edge 10, if I remove, then again number of faces is same, number of components increasing by 1. Okay, so this will happen when edge which is not part of cycle, edge which is not part of cycle. When I remove edge which is not part of cycle. So these things are important. They can ask you MSQ question from this, yes or no? Very nice MSQ questions can be created on these small points. Is this clear? Remember, very nice MSQ questions can be created on these things. So this is the conclusion. This is the conclusion. Finally, this is the conclusion. And this conclusion is very important, that if your graph is planar, if your graph, okay, if your graph G, it is only applicable for graph planar. Okay, if your graph G is planar, okay, with number of faces equal to F, number of faces equal to F, and number of components is equal to what? Number of components equal to C. Then, okay, then on the next page. So if your graph is planar, such that it should be a planar graph, such that with number of faces F and number of components equal to C, then this will happen. Then this will happen. G minus 1 edge, G minus 1 edge, which is part of cycle, which is a part of some cycle, which is part of some cycle. Okay, then what will happen? For this G minus 1 edge, which is part of some cycle, then what will happen? Number of faces decrease by 1. Now the number of faces will become F minus 1. Number of components will be same. Number of components will be same. And if I remove one edge, which is not part of cycle, which is not part of cycle, which is not part of any cycle, then number of faces will not change, but the number of components will increase by 1. Okay, this is clear. This conclusion, these nice questions they can ask. These are very simple questions that can come in the MSQ question. MSQ. Okay, connected, disconnected does not matter. Arpan, did you watch the last video, planar graph? Did you watch it? Did you watch planar graph video? Okay, so did everyone understand? Those students who have watched the last video, did you understand? Tell me, those students who have already watched the last video. So these points, very simple points. So you can notice one thing, that this is the idea. Idea is very simple, that this is your Euler formula. Euler formula is this. In Euler formula, what happens? See, Euler formula is very balanced. If you notice, Euler formula is very balanced. How it is balanced? Notice how it is balanced. This is your Euler formula. V plus F is equal to C plus E plus 1. This is your Euler formula. This is balanced. Why this is balanced? Because if you remove one edge, then the Euler formula will balance itself. This is balanced when you remove edge. When you remove edge, when you remove or add, okay, either you remove or you add one edge. Add one edge in a planar graph. In a planar graph. Okay, so this is actually very simple thing. What I'm saying, this formula is balanced. This formula is balanced when you remove or add one edge in the planar graph. Because see what will happen. If you remove one edge, okay, you are removing one edge. Let's remove one edge. This is your original formula. Let's assume this is your graph. And in this graph, you have V plus F is equal to E plus C plus 1. Let's assume this is the graph. Now, let me remove one edge. From this G, I am removing one edge. Okay, one edge which is part of cycle. One edge which is part of cycle, which is part of some cycle. Now what will happen if I do this? If I do this, then what will happen? This is your graph. In this graph, you have this. Let's assume this is a planar graph. Let's assume you have a planar graph. In this planar graph, you have this thing. Now, if I remove one edge, then what will happen? Then you can notice that the number of vertices will be same. And number of vertices will be same. And number of faces will decrease by, number of faces will decrease by 1. Number of faces will decrease by 1. Number of edges will decrease by 1. Number of components will be same. So again what you got? Again what you got? Again, so the formula is balanced, yes or no? Because you are removing one from here, one from here. So the formula is again balanced. Okay, the formula is, you can very easily see the formula is balanced. You are removing one from here, one from here. So the formula is balanced. And similarly, if I delete one edge, which is not part, which is not part of any cycle, then number of vertices will be same. Number of faces will remain the same. Number of edges is decreasing by 1. Number of components increasing by 1. Again, there is a balance. Again, there is a balance. Again, there is a balance. Okay. So this is the idea behind this Euler formula. This is the idea. This is the proof of Euler formula actually. This is the proof that if you remove one edge or you add one edge in a planar graph, if you remove one edge or you, if you remove one edge, okay, actually, I should say remove one edge. From a planar graph, if you remove one edge, from a planar graph, then it will be balanced. It will balance itself. Okay, it will balance itself if you remove one edge from a planar graph. Is this clear? Very simple. You remove one edge, it will balance itself. Saurabh is saying how to remember Euler formula. That I see. I told you the proof, Saurabh. I told you the proof. I told you the idea. Like this idea, I told you that if you remove one edge, then Euler formula will balance itself. You can think like this, Saurabh. This is how you can remember. See, if you write some different formula, then just remove one edge and see what will happen. If you, for example, what formula you get by mistake? By mistake, if you write this formula, let's assume you write this formula. Then by mistake, if you write this formula, let's assume by mistake, if I write this formula by mistake, then how to check this is wrong formula? Tell me, anyone, how to check whether this is wrong formula? Delete one edge, which is a part of cycle. Delete one edge, which is part of cycle by mistake. If you write this formula by mistake, okay, for planar graph, if you write this formula by mistake, then what you do? How to check? Tell me how to check, how to verify that this is wrong. How to verify that it is wrong? How to verify it is wrong? Just delete one edge. How to verify it is wrong? Very simple. Delete one edge. Okay, which is a part of cycle. Delete one edge which is part of some cycle. Then, okay, then then formula should balance. This formula should balance, yes or no? Then formula must balance itself, yes or no? Must balance itself. Agree? The formula must balance itself. Now, will it balance? Tell me, this formula, will it balance itself? So by mistake, if you write this formula, then will it balance itself? By mistake, you write this formula, like you write this E plus F. This is what you are writing. E plus F equal to V plus C plus 1. Okay, then if you delete one edge, so from this G, I am removing one edge, one cycle edge, I can say. One cycle edge I am removing. Okay, one cycle edge I am removing. Then what will happen? I am removing one edge. If I remove one cycle edge, then number of faces should decrease by 1. Or number of faces should decrease by 1. Number of faces should decrease by 1. Not balance. Not balanced. So this formula is wrong. Okay, like this. Anyway, this actually you can remember this is a simple formula. Then okay, there is nothing complicated in this formula. You can okay, maybe you can make a trick. You can create a trick or easily. This Euler formula for planar graph. You can make some trick for planar graph. So this is the for example, V plus F is equal to E plus C plus 1. VFEC, some trick you can create, like VFEC. Okay, maybe some trick you can create. Is this clear? You can create some trick, you know, in the periodic table. How do we do this? Video conf. Okay, in the periodic table, how do we do this? You know, we create a trick. We create a trick like hydrogen, lithium. Okay, some trick we create, some song we create. Okay, so like that you can create some song, maybe. Okay, whatever. Okay, this EC you can think like this. EC, on one side you have EC, on one side you have electronics, EC, whatever. Okay, so on one side you have EC. Now tell me, if you have connected graph, for connected graph what will happen? Tell me. For connected graph what will happen? For connected graph C will become 1. For connected graph C will become 1. So V plus F is equal to E plus 2. V plus F equal to E plus 2. For connected graph this will happen. Okay, so this is the idea. So this is your Euler formula. The proof we have seen, remember. Okay, remember the proof we have seen. And I told you the proof. The proof is like this. Suppose we remove an edge. Either the number of faces will reduce by 1 or the number of components will increase by 1. In each case, the formula is balanced. In each case, the formula is balanced. In each case, the formula is balanced. This is your proof. Okay, so this is the proof. In each case, the formula is balanced. Very simple. And this fact is important. Please, this fact is important. Like in the GATE exam, I can guarantee that one day this question will come. One day this question will come. They will ask for planar graph. Okay, and there will be 4 options. And they will ask you, you have a planar graph. From that planar graph, if you remove one edge, which is cycle edge, then what will happen? Number of faces will decrease by 1. If you remove one edge, which is not cycle edge, then number of components will increase by 1. So there will be 4 options. And this will be a MSQ question. I can guarantee it will come. Because these things, like, okay, many students, they will just by heart this formula. But these small fact, the proof is not important, but these small facts are important. Yes or no? Agree or not? These small facts, all okay, very, I can say this important part of this proof, important part of a proof. Okay, anyway, let's move on now. We have also seen this in the last class. I told you, in the last video, I told you that this is the relationship. If you have any planar graph, these two important formulas, or I can say two important and proof we have seen actually. So I will not tell you the proof, but two important I can say results. Two important results. What are these? The first result is that for any connected planar graph, this will happen. For any connected planar graph, if you have any connected planar graph with number of vertices must be greater than equal to 3. Okay, number of vertices must be greater than equal to 3. So if you have a connected planar graph, this must be connected and this must be planar and number of vertices is greater than equal to 3. Then what will happen? Then you can notice that number of edges is less than equal to 3n minus 6. Then number of edges is less than equal to 3n minus 6. This will happen. And why this happens? Can anyone tell me why? Why this happens? Do you remember why this happens? Because if you have connected planar graph, just think about it. If you have, and this is the reason it happens, because if you have connected planar graph with n is greater than equal to 3, then what will be degree of every face? Then what will be degree of every face? Degree of every face will be greater than equal to 3, right? Then degree of every face will be greater than equal to 3. Very simple. This is the reason it will happen. Okay, because the degree of every face will be greater than equal to 3 if you have a connected planar graph with n greater than equal to 3. But remember, if n is not greater than equal to 3, then you can notice that, for example, if n is equal to 2, then what is the degree of face? Then what is the degree of this face? Degree of face is 2. Okay, there is only one face, degree of face is 2. And similarly, if n is 1, then again, now what is the degree of face? Now the degree of face will be 0. Okay, so this is the idea. So I am saying that if you have a connected planar graph with number of vertices greater than equal to 3, then degree of every face will be greater than equal to 3. This is the reason this will happen. And the proof you can see in the last class. But this is the reason. This is important. This reason is important. Okay. The next thing, if you have a connected planar graph with a number of vertices greater than equal to 3 and no triangle, no triangle means no cycle of length 3 and no cycle of length 3. Then what will happen? In this case, what will happen? In this case, you can notice number of edges. In this case, number of edges is less than equal to 2 into number of vertices minus 4. And why this happens? And what is the reason why this happens? So again, why this happens? The reason is because if there is no triangle, then what can you say about degree of every face? Because since there is no triangle, so, and also number of vertices is greater than equal to 3. So the degree of every face will be greater than equal to 4. This is the reason this will happen. Okay, so everyone is answering correct. So you understood the last lecture, right? Because everyone is giving correct answer back to back. Okay, with reason you are telling the answer, like degree of face is greater than equal to 4 here. Okay, so I'm very happy. Okay, so this is the idea. So remember, these theorems are one way. These statements are one way. All these statements, and this we can prove. K5, K33, these are not planar. So how to prove it? How to prove that K5 is not planar, right? K5, this K5 is not planar. What is the reason this is not planar? Because if it is planar, then what should happen? Tell me. K5 is not planar. Okay, what is the proof? If it is planar, then what should happen? If K5 is planar, then what should happen? If this is planar, then what should happen? Number of edges should be less than equal to 3n minus 6. This should happen. 3v minus 6. Yes or no? If K5 is planar, then this should happen. Then this should satisfy. But does it satisfy? But you can notice number of edges is 10 and number of vertices is 5 minus 6. Okay, does not satisfy. But you can notice this does not satisfy. So this is the reason K5 is not planar. Similarly, K33. This K33 is not planar. What is the reason? What is the reason that K33 is not planar? K33 is not planar, and the reason is, if it is planar, then what should happen? If it is planar, then what should happen? Remember, this is your bipartite graph. So there is no odd cycle. So there is no triangle. Yes or no? Yes or no? There is no triangle. I can say K33, this is a bipartite graph. K33 is a bipartite graph. And bipartite graph automatically means what? Automatically means no odd cycle. No odd cycle automatically means no C3, no triangle. Okay, because no triangle, so number of edges should be less than equal to 2v minus 4. What is the number of edges? But what happens? Number of edges is actually 9, and that is less than equal to 2 into 6 minus 4. Okay, so that is a contradiction. But this does not satisfy. Not satisfy. This does not satisfy. Okay, so this is the idea. Tell me, what about what about hypercube graph? This is my question. Hypercube graph is can I say this is planar? Can I say hypercube graph is planar? This is my question. Q3. Can I say hypercube graph is planar? Can we say hypercube graph is planar? The answer is if n is less than equal to 3, then Qn is planar. Then Qn is planar. And if n is greater than equal to 4, then Qn is not planar. Then it is not planar. Okay, because so this is this planar? Is this Qn planar? You can notice Q3 is planar. This Q3 is planar. You already know this because this is your Q3. This is your Q3, and this Q3 I can draw like this. The same Q3 I can draw like this. So this Q3 is planar. Without edge crossing, I can draw. Okay, so this is definitely planar. What about Q4? What about Q4? Q4 is not planar. What is the proof? Q4 is not planar. What is the proof? Because again, if it is planar, you know that Q4 is bipartite. Q4 is bipartite, right? Every Qn is bipartite. So Q4 is also bipartite. And because bipartite, so it means no odd cycle. So there is no odd cycle. There is no odd cycle, so there is no triangle also. There is no triangle also. Okay, so if Q4 bipartite, if Q4 is planar, then what should happen? Then what should happen? Then then I can say E must be less than equal to 2v minus 4. This should satisfy. This should satisfy. Does it satisfy? But does it satisfy? Number of edges in Q4, how much? Number of edges in Q4. What is the number of edges in Q4? Tell me. Every vertex has degree. Every vertex has degree what? 2 power n. Every vertex has degree how much? Degree of every vertex is how much? Degree of every vertex is 4. You know, degree of every vertex is 4. So you can find what is the number of edges in Qn. Number of edges in Qn. What is that? You can notice that this is a regular graph. This Qn is a regular graph. You already know. This is a regular graph. So that is the reason I can say number of edges must be equal to total degree divided by 2. Total degree divided by number of vertices. Total degree divided by 2. Number of edges should be this. And what is total degree? Every vertex has degree n, and there are 2 power n vertices. So this will be the number of edges. So the number of edges will be n into 2 power n minus 1. This is the number of edges. So you can notice number of edges will be n into 2 power n minus 1, 4 minus 1. Is this less than equal to 2 into number of edges 2 power 4 minus 4? Is this satisfy? Does it satisfy? Does it satisfy? Like 4, this is 2 power 2. Okay, so does it satisfy? Tell me. Not satisfy. Why this not satisfy? Because what is this value? This value is 28. Okay, this value is 28, and this value is 32. So this does not satisfy. So that is the reason. This is not planar. So remember hypercube graph. This hypercube graph is planar. This is planar if and only if n is less than equal to 3. Okay, very simple. This is another question, and this is a standard question. Every planar graph has a vertex of degree at most 5. Every planar graph, if you have a planar graph, then one vertex, some vertex must have degree less than equal to 5. Means this basically means that every planar graph, it simply means that every planar graph has some vertex with degree less than equal to 5. Okay, so how to prove it? This is okay. What comes to your mind when you see this statement? Like, what do you think? What should I do? What should I do? Prove by contradiction. Yes or no? Prove by contradiction. Very good. Nikhil, very good. Excellent. So prove by contradiction. Assume every vertex has degree greater than equal to 6. Assume every vertex has degree greater than equal to 6. Then what will happen? Assume you have a G is planar. Okay, this. So you can notice. Let's assume G is planar graph. This is a planar graph. Okay. In this planar graph, let's assume every vertex has degree. Assume every vertex. Okay, I can say minimum degree. I can say minimum degree is, let's assume that is greater than equal to 6. Okay. Assume minimum degree is greater than equal to 6. Then this same statement, actually, if you notice this same statement, I can also write that the minimum degree of planar graph. The same statement I can write like this. Yes or no? The minimum degree of planar graph should be what? The same statement I can write like this. The minimum degree of planar graph is okay, less than equal to 5. Yes or no? The same statement I can write like this. Now what I'm saying, assume that minimum degree is greater than equal to 6. Assume, just for contradiction. Okay, for contradiction I'm assuming that every vertex has degree greater than equal to 6. Now what should happen? If this happens, then what should happen to the number of edges? You know, number of edges should be less than equal to what? Okay, you know the handshaking formula. The handshaking formula you already know. I told you that this thing you already know. The handshaking formula you already know. That total degree, this you already know, total degree is equal to twice the number of edges. And also you know that number of vertices multiplied by minimum degree, that is less than equal to 2e. These things we already know. Okay, so number of vertices multiplied by minimum degree minimum degree is 6. Okay, you are assuming minimum degree is 6, so that should be less than equal to twice the number of edges. So from here I can say number of edges is what? So from here number of edges is greater than equal to 3v. This is by handshaking formula. This will happen for all the graphs. This happens for all graphs. This happens. You already know this. For all graphs, this happens. Total degree is equal to twice the number of edges. And we know that n into delta, minimum degree, that is less than equal to 2e. So this we got. And because G is planar, then what should happen? Because G is planar, so what should happen? Because G is planar, so E should be less than equal to 3v minus 6. Can you notice there is a contradiction? Can you notice there is a contradiction? So we got a contradiction. Yes or no? This is saying that E is greater than equal to 3v. This is saying, and this is saying E is less than equal to 3v minus 6. So there is a contradiction. Okay, there is a contradiction. So I can say, because there is a contradiction, So I can say that minimum degree in a planar graph should be less than equal to 5. Okay. Minimum degree in a planar graph should be less than equal to 5. This is the idea. Okay. Is this proof clear? So minimum degree of a planar graph, is less than equal to 5. These proofs are very simple. All these proofs. Okay. The next is four color theorem. What is this four color theorem? So should we take a break? Actually, I want to complete this today. So let's take a 4-minute break. After that, we will come back. 5-minute break. Okay. So we will resume in 5 minutes. We will resume at 10:46. Okay. We will complete this today. Hi everyone, welcome back. Let's see this next. Four color theorem. What is this saying? So this is basically the name itself is telling you. The name of the theorem is saying for planar graph, the chromatic number is at most 4. At most 4. So this is the idea. The chromatic number of any planar graph is at most 4. And this theorem is actually very interesting. In computer science, this theorem has great importance. What is the reason? This is the first theorem which was proven by computer. This is the first theorem which is actually proved by using a computer. So actually, the proof of this theorem is not accepted by many people. Okay, even today, there are many people. Okay, there are many people who don't consider the proof. Okay, they don't consider the proof because the proof is not not done like mathematically. The normal proof, how do we do? Like, okay, the humans do the proof. Okay, we will write some things and we will do. Okay, so for this theorem, the proof is by computer. Okay, and so actually this is also, let me tell you one more thing. Actually, this is not easy to check also. Okay, this computer proved it, but without using computer, okay, like if a human want to check it, then it is not easy, and it is actually very hard. So anyway, this is the proof. Four color theorem means the chromatic number of any planar graph is at most 4. Is this clear? The chromatic number of any planar graph is at most 4. So this is your four color theorem. I can say that okay, tell me, is this statement correct? If I say this, every planar graph is 6 colorable. Is this statement true? 6 colorable. Is this statement true? Every planar graph is 6 colorable. Is this statement true? Of course. Every planar graph is 5 colorable. That is also correct. 4 colorable. That is also correct. 3 colorable. That is not correct. Okay, 3 colorable, that is not correct. So every planar graph is 5 colorable, yes. Every planar graph is 4 colorable, yes. Every planar graph is 3 colorable, that is no. So basically, this is the idea that chromatic number is less than equal to 4. So this is the chromatic number of any planar graph is at most 4. Which of these graph is planar? Which of these graphs is planar? This is your K33. This is your K33, and this is not planar, we already know. This is your Q3. This is planar, we know. And this graph is actually very easy to planar. This is actually very easy planar because what you can do, you can remove this as, oh, sorry, let's see. Is this graph planar? What do you think? Is this graph planar? This G3, is this graph planar? So, is this graph planar? Why this is not planar? This graph. This graph is planar or not? So, for example, can we make a planar representation from this? I don't think we can make a planar representation from this. So how to say that this is not planar? Yeah. Oh, it is K33 actually, right? It is your K33. This is your K33 actually. Because if you see A, B, C, D, E, F, then what I can do, I can put A here. Okay, if I put A here, then this B will go here, this C will go here, and this E will go here. And you can notice that B, C, E, they don't have any A's, there is no problem. And then you can put D here, F here. So this A is, okay, and this D is BCE. Yes, this is actually K33. Yes. So again, this is not planar. This is not planar because actually this is also K33. This graph is also K33. So that is the reason this is also not a planar. Also, okay, if by chance, if you don't get this idea that this is K33 or not, you can check C. Okay, you can see. You can try to make it planar. You can try to make a planar representation and you will not be able to do this. But the good idea is that this is K33, and because this is K33, so this is not a planar. This graph is actually K33. You can notice A is adjacent to all of them, D is adjacent to all of them, and similarly, this finally this F is also adjacent to all of them. So this is your question. Okay. Now this next topic is Kuratowski theorem. The name is, I think the name is Russian, Kuratowski theorem. Okay, so what is this? Actually, let me tell you one thing. Only the statement will be asked. In the GATE exam, they will only ask the statement. So you don't have to worry about anything else. Only the statement they can ask. Okay, so this statement, what this statement is saying, let me tell you that. Do you know that these are the graphs that are not planar? These two graphs are not planar, right? K33 and K5. These are not planar. And there is one more interesting point. These are not planar, and these are the smallest non-planar graph. These are the smallest non-planar graph. These are the smallest non-planar graph. And also one more interesting thing. Every non-planar graph has one copy of one of them. So basically, these are the core reasons for non-planarity. These are the reasons for non-planarity. So you can notice that what is the smallest, like, okay, what is the smallest non-planar graph? If anyone asks you, what is the smallest non-planar graph? If I ask you smallest non-planar graph, number of vertices, like, okay, with respect to number of vertices, who is the smallest? With respect to number of vertices, the smallest non-planar graph is K5. And with respect to number of edges, that will be 3,3. These are the smallest non-planar graphs. And also one more very interesting thing, that these are the reason for non-planarity. These two graphs are the reason. These two graphs are the reason for non-planarity. These are the reason for non-planarity of any graph. These are the reason for non-planarity of any graph. These two. Okay. So this is a theorem. This theorem says that a graph is non-planar if and only if, this is a if and only if theorem. A graph is non-planar if and only if it contains a subgraph which is homeomorphic to K5 or K33. See, one statement you can easily create. Tell me this point. You know that K5 is not planar. You know this is not planar. This is not planar because this K5. Then tell me any supergraph of this K5. What can I say about any supergraph of K5? What will happen to that? What will happen to that? Any supergraph of K5. Any supergraph of K5 means, okay, to the K5, if you add something more, if you add some vertices, some edges, if you add some more vertices. So see, this K5 is not planar. This K5 itself is not planar. Then any supergraph of K5 is also not planar. That is also not planar. So because you can notice that, let's assume this is your non-planar. See, this graph K5, this is your K5, and this is non-planar. This is the graph K5. Okay, so like this is your graph. So something like this. Okay, you can just check it. So this type of graph you have. Now this is a non-planar. Now if I add some more vertices and some more edges, if I do some more vertices, edges, then what can I say? Then this also will be not planar. Why? What is the reason? Because you cannot represent this. Think about it. Yes or no? This is your K5 and this is a super graph. Now you cannot, this you cannot represent in a plane. This you cannot represent without edge crossing. This itself you cannot represent without edge crossing. Okay, obviously. So that is the reason I can say this is non-planar. So I can say I can say, this is the statement I can say. If G has a subgraph, if G has a subgraph which is isomorphic, this is a statement. Okay, if G has a subgraph which is K5 or K33, which is isomorphic to K5 or K33. If G has a subgraph which is isomorphic to K5 or K33, then what should happen? If G has a subgraph which is isomorphic to K5 or K33, then what should happen? Then G is not planar. Then G is not planar. Then this graph G is not planar, right? Yes or no? Then definitely G is not planar because G has a subgraph which is K5 or K33, which is isomorphic to K5 or K33. Then this is not planar. But the reverse direction is not correct. The reverse direction is not correct. Also, this same statement, how can they ask you this same statement? This statement is very easy. This statement you can very easily see. If you have a graph G which has a subgraph, so your graph G is like this. This is your graph G, and in this graph you have K5. Let's assume this is your K5. Then you can clearly see that this G is not planar. Obviously, because you cannot represent this K5. You cannot represent this K5 without edge crossing. So this is the idea. So G is not planar. This is very easy. The same statement they can ask you in another way. What is that? The same statement they can ask you. Like this, if I ask you, if G has clique number, if G has clique number greater than equal to 5, if G has clique number greater than equal to 5, then what I can say? If G has clique number greater than equal to 5, it automatically means what? It automatically means there is a subgraph K5. It automatically means there is a subgraph. It automatically means there is a subgraph K5. Yes or no? If you have clique number, greater than equal to 5, then it means there is a subgraph which is K5. Okay, so then G will be what? Then G is not planar. Then definitely G is not planar. Okay, so these things. Now let's see one more thing. So you know that, okay, this statement is actually not correct. Which statement? So if G has a subgraph, if G has subgraph K5 or K33, if G has subgraph K5 or K33 isomorphic, if G has subgraph K5 or K33, then G is not planar. This you already know, there is no problem here. But when we say that G has K5 or K33, then what we are saying? Then basically what we are saying isomorphic. Okay, then basically we are saying that isomorphic to K33 or K5. Oh, so if G has a subgraph isomorphic to K33 or K5, then what can I say? Then I can say G is planar. But reverse is not true. But converse is not true. Converse is not true. Converse is not true. What it means? Converse is not true. What it means? If a graph is non-planar does not imply, okay, not planar does not imply, okay, a subgraph which is K5 or K33. Non-planar does not imply a subgraph which is K5 or K33, which is isomorphic to K5 or K33. Is this clear? Okay, so this is what Kurotasky theorem says. Actually, there is something called homeomorphic. This Kurotasky theorem says that a graph is non-planar if and only if it contains a subgraph homeomorphic. First of all, this is homeomorphic. First of all, this is different from isomorphic. This is not, remember, this is not isomorphic. First of all, this is not isomorphic. Also, this is not homomorphic. These are different. Homomorphic. These things are different. This is out of syllabus, so you don't have to worry. This is out of syllabus. So we will not worry about this. But I am saying that this is different. Homeomorphic is different from homomorphic and isomorphic. The same statement, if I change it to isomorphic, the same statement, if I change it to isomorphic, then this statement is wrong. The same statement, if I make it isomorphic, then this statement is wrong. Now this statement is wrong. If I do this, okay, this is a wrong statement. This statement is false. Why this statement is false? Which direction is correct? Which direction is correct? If or only if. This statement is false, but which direction is correct? Okay, for example, which direction is correct? Like, can I say this is, now tell me, is this statement correct now? Is this statement true or false? A graph is non-planar if it contains a subgraph. This statement is true, right? Yes or no? A graph is non-planar if it contains a subgraph K5 or K33. Very simple. A graph is non-planar if it contains a subgraph which is K5 or K33. This is true, but this statement is false. If I remove, like, okay, this only if statement, this will be false. Now this statement is false. And this homeomorphic is two ways. If you have this homeomorphic, then this will be two ways. So this is your statement. I just want to tell you that this is the Kurotasky statement. And this is what you need. Basically, you need to by heart this statement. This statement you need to by heart. Okay. The proof, if you ask me, how long is the proof? Let me tell you. The proof is almost the shortest proof. That will be almost 5 or 6 pages long. The shortest proof. 5 or 6 pages long. Okay. So basically, by the time you go to the end of the proof, you will forget what happened in the beginning. Okay. So this proof is very complicated. This proof is so complicated that even in the IISc graph theory course, they don't teach the proof. They don't teach the proof. They will just give the idea. They will give some idea. They will not teach the complete proof. So, okay. So this is anyway. So don't worry about this proof. The idea is very simple. So this is your GATE exam question. GATE 1990. Which statement is correct? A graph is planar if and only if. A graph is planar if and only if. If and only if. Okay, a graph is planar if and only if. It does not contain a subgraph homeomorphic to K5 or K33. This statement is correct. Remember, this statement is not correct. Okay, this statement is not correct. Is this clear? It does not contain subgraph isomorphic to. These two statements are same, right? Option B, option C, how they are same? Option B, option C. A graph is planar if and only if it does not. Yeah, and yes, this is correct, right? Option A is correct. Option A is correct. A graph is planar if and only if it does not contain this, neither this nor this. Yes or no? Neither this nor this. Neither this nor this. The same statement, remember, the same statement if I do like this, a graph is non-planar, then what will happen? If I say a graph is non-planar, then what will be correct statement? And let's assume, okay, let's assume I remove this node. Now what will be the correct statement? A graph is non-planar. A graph is non-planar if it contains either this or this. Now this is correct. A graph is non-planar if either this or this. If either this or this. But a graph is planar, neither this nor this. Does not contain homeomorphic to this or this and this. Okay, I think this statement should be and. I think this should be and. I think this should be and. Okay, so this statement is also not correct, and this statement is also not correct. Is this clear to everyone? Please tell me. Is this clear? Okay, so this homeomorphic word is important. One more thing. In the same question, if I make this, now what should be the answer? Same question, I am doing this. A graph is planar, if it does not contain this, yes. So this is also correct. This will be correct. There is no problem. This statement A this A statement will be correct always. This statement is if and only if this homeomorphic does not contain homeomorphic to this and this. This is both ways. But now this statement will also be correct. If I put and here, okay, now this statement will also be correct. Is this clear? Still, this statement is not correct. This statement is not correct. And in the same question, if I change this only if, in the same question, if I make it only if, now what will happen? This statement will be correct. There is no problem. This statement will be correct. All other statements are wrong. All other statements are wrong. Is this clear to everyone? Please tell me. Is this clear? And one more thing actually you need to see. Tell me one thing. Every subgraph of planar graph, what can I say? Every subgraph of planar graph. Every subgraph of planar graph. What do you think? Every subgraph of planar graph is planar. Every subgraph of planar graph is planar. Because if you have a planar graph, just think about it. You have a planar graph. Your graph is planar. Your graph is planar. This is your graph. Let's assume this is your graph. And this graph is like planar. Let's assume. So there is no edge crossing. There is no edge crossing, right? Okay, so there is no edge crossing. So there is no edge crossing. Okay, because there is no edge crossing. So G is planar. It means there is no edge crossing. There is no edge crossing. So if you create a subgraph, now from this, if you create a subgraph, then also no edge crossing. Then also no edge crossing. Then also no edge crossing, right? If you create a subgraph, then also no edge crossing. So every subgraph of planar graph is planar. Okay, actually, let's come back to this question. I think some confusion is there. See, this statement we know that. Okay, let's come back to this question. This statement we know that a graph is planar. Or I can say a graph is non-planar. Let's see this. A graph is non-planar if and only if no subgraph homeomorphic to. A graph is non-planar if and only if and only if there is subgraph. There is some, if and only if there is some subgraph. There is some subgraph homeomorphic to whom? Homeomorphic to whom? Homeomorphic to K5 or K33. Yes, this statement is correct. A graph is non-planar if and only if there is some subgraph homeomorphic to K5 or K33. The same statement, how do I write as planar? So how do I write it as planar? A graph is planar if and only if there is no subgraph homeomorphic to. A graph is planar if and only if there is no subgraph homeomorphic to this or this. Yes, this is correct. This statement is correct. Okay, a graph is planar if and only if there is no subgraph. We don't have any subgraph which is homeomorphic to, there is no subgraph which is homeomorphic to K5 or K33. Yeah, okay, so this is correct actually. This is correct. Okay, yeah. So here actually there should be, the answer will be, so a graph is non-planar if it contains a subgraph homeomorphic to K5 or K33. This is correct, option D. And here actually option D will be correct. Okay, sorry. Here option D will be correct. Option D will be correct. Option A will not be correct. Option D will be correct. Option A will not be correct. Tell me, did you understand this? Did you understand this? This statement, did you understand? See, a graph is non-planar. A graph is non-planar if you have some subgraph which is homeomorphic to this or this. Now, when can I say a graph is planar? Just think about it. When can I say a graph is planar? Planar graph means what? Planar graph, if and only if, it means what? There is no subgraph in this. There is no subgraph. There is no subgraph which is K5 or K33. There is no subgraph which is K5. Okay, there is no subgraph which is K5 or there is okay or K33. Yes or no? There is no subgraph which is K5 or K33. So this is the statement. So these two statements you can see. There is no subgraph which is homeomorphic to K3 or K5 or K33. So actually for this question, option D will be correct. A non-planar, okay, and yeah, so option D will be correct actually here. So this option A will not be correct. Option D will be correct. And here also option A will not be correct. A will not be correct. Option D will be correct. There is a confusion in or and and. So let's see. Just tell me, what should I write? Okay, should I write this? Like if I write this statement, what it means? If I write and here. If I write and here, what this means? Just read this statement. This statement is saying that a graph is planar if and only if there is no subgraph, homeomorphic to this and this. Homeomorphic to this and this. Homeomorphic to this and this. See, this statement is false because you can notice if I take this graph, like if I take this K5, in this K5, do we have a subgraph? Just tell me this point. Okay, please tell me this point. Do we have a subgraph? Do we have a subgraph which is, don't worry about homeomorphic. I will tell you what is homeomorphic. Don't worry about it. Okay, don't worry about it. But just tell me this point. In this K5, let's assume this is your graph K5. K5 is your graph. In this graph, do we have a subgraph which is homeomorphic? Okay, like, okay, don't worry about homeomorphic. Just tell me the isomorphic. Tell me about isomorphic, which is isomorphic to, for a moment, think about homeomorphic as isomorphic. I will tell you the definition, but think about it, isomorphic. So do we have subgraph which is isomorphic to, K5 and K33? Tell me, K5 and K33. Tell me this, Nikhil. Nikhil, tell me this. Is there any subgraph? Nikhil, is there any subgraph? Is there any subgraph which is homeomorphic to this and this? Is there any subgraph which is homeomorphic? Okay, think about homeomorphic as isomorphic. Don't worry about homeomorphic. Think as isomorphic. So in this, do we have a subgraph which is isomorphic to K5 and K33? The answer is no. The answer is no. The answer is not. But K5 is planar. But K5 is non-planar, right? So now is this clear? Now is this clear? So this statement is actually false statement. This statement is false. Now is it clear? Please tell me. Okay. So this statement is correct. A graph is planar if and only if there is no subgraph which is homeomorphic to K5 or K33. And a graph is non-planar if there is some subgraph which is homeomorphic to K5 or K33. So this is the idea. And you can notice every subgraph of planar graph is planar. Okay. Is this clear? Now, let's see this. Some students are talking about homeomorphic. Okay, like what is homeomorphic? So actually this topic is optional. That is the reason I have given this optional. So what I am going to teach now, that is completely optional, completely optional. So if you want to go, you can go. You don't have to study this. Okay, please don't get any doubt in this. So this is optional and this you should skip. You should definitely skip this. So don't worry about what I'm going to teach now. Basically, I'm going to teach what is homeomorphic. And this I'm teaching only because of your curiosity. Like some of you might be curious, what is this homeomorphic? What is the difference between isomorphic, homeomorphic? Some of you might be curious. So for that curiosity, I'm teaching you this. But remember, this is optional. So don't study this. If you study this, don't worry about it. If you understand or if you do not understand, don't worry about it. Don't ask me any doubt from this topic. Don't get any doubt from this topic. Don't do any research in this topic. Okay, just one time you study this and forget about it. So what is this? This is homeomorphic graphs. What is the meaning of homeomorphic graph? Let's see. So this is your, actually for this question, I am explaining this. Like what is this homeomorphic? This is what I want to explain. So let me tell you first, before we see the next concept, let's see what is subdivision of a graph. The first concept we need to see, this is optional. Again, not required for GATE. Again, not required for GATE. Not needed for GATE. Skip. Not needed for GATE. Okay. But let's see what is this subdivision. What is this concept? Subdivision of a graph. The name itself is telling you subdivision. Subdivision. So you are dividing the age. Basically, you are dividing the age. What is subdivision? Subdivision. What is the subdivision? Subdivision is basically you are dividing the age. Subdivision. It, like for example, if you have age, if you have this age, then what will be the subdivision? Then what will be the subdivision? Like this is your age and you are dividing this age. This age you are dividing. Like, okay, you are making some more vertices. This is the idea. Is this clear? You are dividing this age. This is called subdivision. Means you are putting some more vertices. V1, V2, V3. Some more vertices you are putting. Some more vertices you are putting. Now you can notice. So basically subdivision means you are replacing this age with a path. This is the idea. What is subdivision? Subdivision means replacing age with a path. Replacing age with a path. So this is the definition of subdivision. Subdivision means what? Replacing age with path. Replacing age with a path. Is this clear? Please tell me, is this definition clear? Very simple definition. Name itself is telling you subdivision. Subdivision means you are replacing, you are dividing this. Like this is your age and you are dividing this. This is called subdivision. This is called subdivision. Like for example, this is another subdivision. This is another subdivision. This is also subdivision. So this is the concept of subdivision. Means you are dividing the age, okay, and you are putting some vertices. Like this is a path, you can think like this. This is a path and some new homes you are creating. Some new homes you are creating here. Some new homes you are creating. So this is the idea. So subdivision means replacing age with a path. This is the concept. So if you have, for example, let's assume you have this graph A, B, C. Then tell me, can I say subdivision of C3 is C5? Can I say subdivision of C3 is C5? This is my question. Can I say C5 is subdivision of C3? C5 is subdivision of C3. Can I say subdivision of C3? Think about it. This is your C3. From this C3, can you get C5? Can you get C5 from this C3? How will you get? See, very easily you can get. What you can do, very easily you can get subdivision. So all you have to do is subdivision. So can you get C5? Yes, I can get C5. What I will do like this. This is your C3. This is your C3. One house I can create. One house I can create here and one house I can create here. Like this. What you got? V, U. So actually this is what you got. You got, okay, this is what you got. A, V, B, C, U, A. So C5 you got. So I can say C5 is subdivision of, yes or no? So C5 is subdivision of C3. Tell me one thing. Cn plus 1 is subdivision of Cn. Is this correct? Cn plus 1 is subdivision of Cn. This is also correct. These two statements are correct. Like I can say Cm is a subdivision of Cn where m is greater than equal to n. Is this statement correct? Can I say C3 is subdivision of C3? All these statements are correct. You can notice. All these statements are correct. All these statements are true. Okay, so this statement is true, this statement true, true, true. All these statements are true. Because C3 is subdivision of C3. Okay, how? Tell me what is the reason? Don't subdivide. Who told you to subdivide? Don't subdivide. Okay, so this is your C3. And if I do subdivision, then I can get C3. Yes, I can replace edge with path. This replace I can edge with path. Every edge is also a path. So this is C3 is okay. And I can get like this also. I can get like this also. V, B, C. This is your C4. Is this clear to everyone? Like what is happening? So you can notice C5 is subdivision of C3 and so on. Clear? Tell me one more question. Like, can I say C3 is subdivision of P3? Can I say C3 is subdivision of P2? Subdivision of P2. Can I say C3 is subdivision of P2? The answer is no. The answer is clearly no. How can you get cycle if you do subdivision? If you do subdivision, this is your P2. This is your P2. If you do subdivision, how can you get cycle? How can you get cycle if you do subdivision? If you do subdivision, how can you get cycle? This is your P3. If you do subdivision, then how can you get cycle? So whatever subdivision you will get another Pn. You will again get Pn, yes or no? So subdivision again will give you Pn. You cannot get, so the answer is no. C3 is not subdivision of P2. Is this concept clear? Subdivision. Now the next concept is homeomorphic. This is the concept, homeomorphic. This is not homomorphic. Remember this, homeomorphic is different. Homeomorphic. This is different from isomorphic. Also, this is different from homomorphic. This is out of the syllabus. We will not study this. I will not tell you this. This is completely out of the syllabus. This is in the syllabus, but less important, very less important. They will not ask you. I can guarantee that they will not ask you. This is in syllabus. This is in syllabus, but what they will not ask. Okay, this is in syllabus, but will not be asked. Okay, why I can say that this will not be asked? Like why I am so confident this will not be asked? Like homeomorphic, this will not be asked. Because the books do not cover it. The reason is this. The standard books that you study, the standard books do not cover it. That is the reason. So in syllabus, this is in syllabus, but it will not be asked. Okay, because the books do not cover, standard books, they do not cover it. All the like Kenneth Rosen and so on. So they do not cover it. Now let's see what is homeomorphic. Two graphs are homeomorphic. Two graphs are homeomorphic if there is a graph isomorphism between some division of G to some subdivision of G dash. So when can I say G and H are homeomorphic? When can I say they are homeomorphic? They are homeomorphic. When can I say G, H are homeomorphic? Homeomorphic. They are homeomorphic if and only if some subdivision of G is isomorphic to some subdivision of H. Some subdivision of G. Is this definition clear? Tell me. Some subdivision of G is isomorphic to some subdivision of H. The definition is clear? Some subdivision of H. This is the definition. So G, H, they are homeomorphic. They are homeomorphic if and only if some subdivision of G is isomorphic. Is isomorphic to some subdivision of H. So for example, can I say these are homeomorphic, C3, C5? What do you think? C3, C5, are they homeomorphic? Are they homeomorphic? You can notice C3 is not isomorphic to C5. This is not isomorphic, but this is homeomorphic. C3 is homeomorphic to C5. Because why they are homeomorphic? Because some subdivision of C3 is isomorphic to some subdivision of C5. Yes or no? Yes or no? Some subdivision of C3. Some subdivision of C3 that is isomorphic to some subdivision of C5. And C5 itself is subdivision of C5. C5 itself is subdivision of C5. So these are homeomorphic, C3 and C5. This is the difference. Did you understand the difference? Tell me. Did you understand the difference between homeomorphic and isomorphic? So can I say every isomorphic graphs are homeomorphic? This, okay, tell me. If G, H are isomorphic, if they are isomorphic, then they are homeomorphic also. Then they are homeomorphic also. If they are isomorphic, then they are homeomorphic also. Very simple. Because G is subdivision of G, H is subdivision of H. Okay, G itself is a subdivision of G. So this is the idea. So remember, you can notice that every graph is subdivision of itself. Every graph is a subdivision of itself. Don't divide any as subdivision of itself. Don't divide any as. Every graph is subdivision of itself. Now you can notice that if they are isomorphic, so isomorphism is homeomorphism. So you can notice every isomorphism is homeomorphism. Isomorphism is homeomorphism. Homeomorphism, but not vice versa. But not vice versa. But converse is not true. Okay, but not vice versa. Converse is not true. If two graphs are isomorphic, then definitely they are homeomorphic. But you can notice that C3, C5, these are homeomorphic. C3, C5, these are homeomorphic, but they are not isomorphic. So this is the definition of isomorphic, homeomorphic. Is it clear? Like these two graphs, tell me, are they homeomorphic to each other? These two graphs, are they homeomorphic? Are they homeomorphic? Are they homeomorphic? Homeomorphic means some subdivision of G is isomorphic to some subdivision of H. Some subdivision of G is isomorphic to some subdivision of H. So which subdivision? So what I can do, I can create subdivision. I can create this subdivision of G. What I can do, I can create, see, very simple. This is your G. This G is like this. This is your G. This is the G that is given to you. This is the G that is given to you. And this is the H that is given to you. Okay, this H is given to you. These two graphs are given to you. Okay, these two graphs. So tell me, can you give me a subdivision? Its subdivision, which are isomorphic. Okay, so yes, I can give subdivision of G. I can give this subdivision of G, I can give. See, I can do subdivision of G. I can do subdivision of G. I am doing subdivision of G. So this is a subdivision of G, yes or no? Please tell me, this is a subdivision of G, yes or no? Because I am replacing the edges by, this is a subdivision of G. Okay, because I am basically, this is what I am doing. This is what I am doing. So this is a subdivision of G. Now give me a subdivision of H. Give me a subdivision of H, which is isomorphic to this. Very easily, just do this. Just do this. Just do this. Just do this. So again, okay, this subdivision. This subdivision. So you can notice, yes, they are isomorphic. Yes, they are isomorphic. Is this clear? Yes, they are isomorphic. Okay, so basically, remember, this subdivision I can create. This subdivision I can create. From H I can create this subdivision. Now you can notice they are isomorphic. So yes, they are homeomorphic. They are homeomorphic. But remember, G is not isomorphic to H. G is not isomorphic to H. G is homeomorphic to H. The difference of isomorphic, homeomorphic, is it clear? Some subdivision of G should be isomorphic to some subdivision of H. Okay, let's see another example. Tell me which of them are homeomorphic. Which of them are isomorphic? None of them are isomorphic to each other, right? None of them are isomorphic to each other. Are they homeomorphic like A, B? A, B, are they homeomorphic? A, B. Check it. A, B. Yes, they are. Yes, they are homeomorphic, right? Yes, they are homeomorphic because if I do this subdivision, then I will get, then they will become isomorphic. If I do this subdivision, they will automatically become isomorphic. So yes, A is homeomorphic to B. A is homeomorphic to B. This subdivision will give you the answer. This subdivision will give you the answer. Okay, this subdivision. Just do this subdivision. This will make the answer. What about A, C? What about A, C? Tell me. What about A, C? Are they homeomorphic? A, C. Yes, they are also homeomorphic. You can do this. You can do this. You can do this. You can do this. Okay. Similarly, B, C. They are also homeomorphic. So all of them are homeomorphic to each other. Yes or no? All of them are homeomorphic to each other. What about these two? Are they homeomorphic? Like here you have a vertex. Are they homeomorphic? And here there is no vertex. This is a straight line. Are they homomorphic? So this is G, this is H. So can I say they are homeomorphic? And the answer is yes. Because you can see, you can create this here, and you can create this here. So they are homomorphic. Kusal, they are homomorphic, right? This subdivision you can create here, and this subdivision you can create here. Now you can notice they are isomorphic. Some subdivision of G is isomorphic to some subdivision of H. Remember, when you are checking homeomorphic, then you can do subdivision on both sides. Some subdivision of G is isomorphic to some subdivision of H. On both sides, you can do subdivision on both sides. Just try to make them isomorphic. Is this clear? Is it clear? And what about these graphs? What about these graphs? So you can notice G1, G2, are they homeomorphic? G1, G2. Two homeomorphic graphs obtained by G by adding vertices. Actually, from this is the subdivision of G. This is also subdivision of G. Both of them are subdivision of G. They both are actually subdivision of G. They both are actually subdivision of G. This is also subdivision of G. This is also subdivision of G. Both are actually subdivision of G. Okay, because how to get G2? How to get G2? Like this, you can get G2. This is your G2. See, this is your G2. If I do this, then this is your G2. And how to get G1? How to get G1? This is your G1. Okay, this is your G1. Now, so this is, if I do this, I will get G2. If I do this, I will get G2. If I do this, I will get G1. Now tell me, G1 and G2, are they homeomorphic? Yes, they are homeomorphic. They are homeomorphic because if I do this and if I do this, now you can notice they are isomorphic. Now you can notice they are isomorphic. Yes or no? If I do this here, and if I do this here, then now you can notice they are isomorphic. Is this clear? They are isomorphic. So that is the reason they are homeomorphic. Yes, you can change in both the graphs. See the definition. Kusal, see the definition of homeomorphic. G is homeomorphic to H. G is homeomorphic to H if and only if some subdivision of G, if and only if some subdivision of G is isomorphic to some subdivision of H. Is this clear? Some subdivision of G is isomorphic to some subdivision of H. Anyway, this is the idea. Okay, you can forget about it. This is just I can say optional. This is just an optional topic. This subdivision, homeomorphic, and all these things. But why these things are interesting? These things are interesting because, okay, this is the interesting thing. Note, this is very interesting thing. See what will happen. Tell me, if I do, like K5 is non-planar, right? Okay, just tell me this point. If I have a planar graph, every subdivision of planar graph is planar. Can I say this? This statement can I say? Every subdivision of planar graph is planar. Of planar graph is planar. Can I say? Every subdivision of planar graph is planar. The statement is true. Why? What is the reason? What is the reason? See, very simple. If you have a planar graph, then every subdivision will be a planar. Like if I give you a planar graph, let's assume your graph is planar. Your graph G is planar. So then it means what? There is no edge crossing. Like, okay, so this type of planar graph you have. So let's assume this type of planar graph you have. Okay, it means what? It means there is no edge crossing. It means what? There is no edge crossing. There is no edge crossing. Now, if you make a subdivision, will you get edge crossing? Tell me, please tell me this point. If you make subdivision, like if you do like this, can you get edge crossing? If you do like this, can you get edge crossing? Tell me. In this G, this is your G. Okay, this is your G. This is the graph G. You can notice. Now, in this graph G, if I make subdivision, if I do subdivision, then again there is no edge crossing. Again, there is no edge crossing. Again, there is no edge crossing. So this is the idea. Okay, so every subdivision of planar graph is planar. Yes or no? And same thing I can say for non-planar also. Every subdivision of non-planar is non-planar. Every subdivision of non-planar is non-planar. Of non-planar is non-planar. Okay, every subdivision of non-planar is non-planar. Means, like if you have a like non-planar graph, like for example, you have K5. Okay, this is your K5. Your K5 is like this. So you have this K5. Or maybe I can do like this. This is the K5. Now tell me one thing. In this K5, if I create a subdivision, will it become planar? If I do subdivision, then also it will become non-planar. This is non-planar. This is non-planar. This structure is not planar. This structure is not planar. If I do subdivision, still there is no change. Still there is no change. Yes or no? If I do subdivision, still there is no change. Still it is non-planar. Now also this graph is non-planar because the structure is not changing. Structure is still the same. Structure will not change. So this is the idea. So you can notice every subdivision of non-planar is non-planar. So finally, what is the conclusion? This is very important conclusion. What is the conclusion? Subdivision does not change planarity. Yes or no? subdivision does not change planarity. Does not change planarity. Yes or no? Does not change planarity. Does not change planarity or non-planarity. Is this clear to everyone? Please tell me. This topic is not important, but this topic is easy. This topic is actually easy. This is not hard. This topic is easy. Like one by one, tell me. Okay, one by one. Did you understand subdivision? First, you tell me, did you understand subdivision? You have A's and you are dividing. You are dividing. This is your subdivision. So the concept of subdivision you understood. The next concept, homeomorphic. Did you understand? Homeomorphic. Two graphs are homeomorphic if some subdivision of this, some subdivision of this are isomorphic. This you understood? The examples that I took. Okay, you have two graphs. Those are homeomorphic if some subdivision of this, some subdivision of this, they are isomorphic. Then that is your homeomorphic. Now this is very simple point that subdivision does not change. This does not change planarity or non-planarity. Okay, if your graph is planar, after subdivision also this is planar. After subdivision also this will be planar. Okay, and if your graph is non-planar, then after subdivision also this will be non-planar. Okay, so this is the idea, because the structure does not change. Like you can notice this is subdivision of K5. This is subdivision of K5. So you can notice this is still non-planar because this does not change the fundamental structure. The fundamental structure does not change. The fundamental structure does not change. Okay, if you have non-planar, then subdivision is non-planar. If you have planar, then subdivision is planar. Okay, next. So this is the idea. So remember, if you do subdivision, then structure does not change. If you do subdivision, then the shape, the fundamental shape does not change. If you notice, the fundamental shape does not change. Like you have a graph. I give you any graph, like this is a graph, let's assume. In this graph, if you do subdivision, then the fundamental structure does not change. That's the idea. You can notice the fundamental structure does not change. For example, if there is a human and that human gets pimples, like these are like pimples, then will the human change? The basic, like can I say the human will change? The internal side of the human will change. So these are like pimples. This subdivision is like a pimple. Okay, maybe you can understand like this, I don't know. Okay, so basically human plus pimple is still the same human. So something like this. These are the pimples. Okay, are you getting this point? So anyway, so the same structure, the fundamental shape of the structure does not change. So this is the idea. So whatever subdivision you make, the fundamental structure, the fundamental shape of the structure does not change. So, okay, now some statements. Now we have some statements and all these statements. So now you tell me what will happen. Then can I say a graph is planar? A graph is planar if and only if every subdivision is planar. If and only if every subdivision is planar. Every subdivision of G is planar. Yes or no? Okay, a graph is planar. A graph is planar if and only if every subdivision is planar. Is this clear? Is this clear? A graph is planar. A graph is planar if and only if every subdivision is planar. Because you know that if graph is planar, then subdivision will be planar. Okay, if graph is planar, you know this. If graph is planar, then subdivision will be planar. And if every subdivision is planar, see, if a graph is planar, then subdivision will be planar. Okay, if a graph is non-planar, then subdivision will be non-planar. Then I can say that if a graph is planar, then every subdivision will be planar. If and only if every subdivision is planar. The same thing I can say like this. A graph is non-planar. A graph is non-planar if and only if some subdivision is what? Tell me. Some subdivision of G is non-planar. Of G is non-planar. Is this clear? A graph is non-planar if and only if some subdivision of G is non-planar. So this is the statement. A graph is planar if and only if. So this type of statement also can come in the GATE exam. They can ask you this statement also. Okay. So you know that subgraph of planar graph is planar. This you already know. Subgraph of planar graph is a planar. And this is another statement. A graph is planar if and only if every subdivision is planar. So I can say a graph is non-planar if and only if some subdivision of G is non-planar. These two statements are same as this statement. So this is the idea. So you can notice Kurotasky theorem can be written in many different ways. This Kurotasky theorem, this you can write in many different ways. A graph is planar if and only if it does not contain a subgraph which is subdivision of K5 or K33. It does not contain a subgraph which is subdivision of K5 or K33. Okay, so there are many different statements for Kurotasky. Yes or no? Either you can use this homeomorphic word or you can use this subdivision word. Okay, both are correct. All these statements, did you understand? Tell me. So remember this Kurotasky theorem, they can ask you in many different ways. They can ask you this Kurotasky theorem. Either they will ask you like this. A graph is non-planar if and only if it contains a subgraph which is homeomorphic to K5 or K33. The same statement they can also write like this. A graph is non-planar if and only if it contains a subgraph. It contains a subgraph that is subdivision of K5 or K33. It contains a subgraph that is subdivision of, it contains a subgraph which is a subdivision of K5 or K33. Okay, so like this. The same statement they can ask in many different ways. Another statement they can ask is like this. A graph is planar. A graph is planar if and only if every subdivision is planar. Every subdivision of G is planar. A graph G is planar if and only if, you can notice, a graph G is planar if and only if every subdivision of G is planar. Okay, so anyway, this is the complete, and this was an optional topic. Again, I am telling you, this was an optional topic. So finally, now you understood. Now you understood the idea of homeomorphic, right? Now you understand the idea of homeomorphic. Is this clear? See, notice that in this graph, if you notice, like, if you notice this graph, in this graph, there is no subgraph which is isomorphic to, in this actually, there is no subgraph. If you notice this graph, then very interesting thing you can notice that there is no subgraph which is isomorphic to, there is no subgraph which is isomorphic to whom? Which is isomorphic to K5 or K33. K5 or K33. Which is not which is isomorphic. There is no subgraph which is isomorphic, but there is a subgraph, but there is some subgraph, or I can say this is subdivision of K33. I can say this is subdivision of K5. This is actually subdivision of K5. This graph is subdivision of K5. So that is the reason I can say that this graph is homeomorphic to K5. Yes or no? This graph is homeomorphic. This graph is homeomorphic to K5. This graph is homeomorphic to K5. This graph is not isomorphic to K5. This is not isomorphic to K5, but this is homeomorphic to K5. So that is the reason here in this question you can notice this statement is correct. A graph is planar if and only if there is no subgraph homeomorphic to this or this. But this statement is not correct. This is the reason. Okay, anyway, this was an optional topic. Please, this homeomorphic subdivision, okay, this homeomorphic and subdivision, this is optional. Whatever I have taught you, whatever I have told you, if you understood that, that is enough. If you did not understand, then also it is fine. Don't worry about it. But one thing is important. What is that? Don't do any research. Don't go to the internet and find out these things. Don't study more. These things, don't study more. After the GATE exam, you can study. In your MTech, you can take graph theory course. In that course, you will study whatever you want, you will study. All these things you will study. Okay? Is this clear to everyone? Again, I am repeating. If you did not understand this optional topic, don't worry about it. If you understood, very good. But do not do any further study in this. Do not do any further research in this. And do not get any doubt in this. Is it clear? Anyone has any doubt, let me know. So this is your planar graph. Everything we have seen, every concept we have seen. Please let me know if you have any doubt. Everything we have seen in the planar graph, every concept. Any doubt, anyone? See, every topic we are clearly understanding. Every topic, planar graph, chromatic number, age chromatic number, okay, independent set, matching, all the concepts we have studied in a very detailed manner. Many examples, many variations, all the GATE exam questions, all the TIFR exam questions, everything we have taken. So please let me know, like, are you understanding this graph theory? This graph theory, did you understand? Okay. Nothing will come outside of these notes. Every concept, like questions, new questions can be created. The GATE exam will create new questions, but the concepts are these. Okay, every small topic, every small point I'm telling you. So if you understand all of these things, then you don't have to worry about the GATE exam. You will crack GATE exam, you will crack TIFR exam, you will crack interview, you will crack everything. Just understand everything that we are learning in the class. And also attempt the weekly quizzes, also attempt the test series. Okay. So once the graph theory is over, then discrete mathematics, all the tests in the Go classes and GATEOverflow, these two test series, GATEOverflow plus Go classes, combined test series, all the tests you have to attempt. Okay. Very nice questions you will find in both these test series, GATEOverflow as well as Go classes, combined test series you should take. Okay. Any doubt, anyone? Kusal, is any doubt? Kusal, Abhipsa, any doubt? Nikhil, Satyajit, Pawan, Ananya, KS, Aditya, AP, any doubt? Okay. Okay, everyone. So in the next 3 or 4 lectures, graph theory will be over. Some topics are remaining. All the classes are scheduled. Tomorrow we have another class. Tomorrow we will study Euler and Hamiltonian Euler and Hamiltonian graph. This concept we will study tomorrow. Okay, and after that we will continue. So once the graph theory is over, all the weekly quizzes, GATEOverflow test, Go classes test. So from the discrete mathematics you should do. Okay. Yes. Yeah. I will start early. Actually. Yes. We will start early. Okay. 7:30 we will start. Tomorrow we will definitely start at 7:30. Okay. Nikhil, any doubt? Any doubt, Nikhil? Let me know what is the doubt. Please raise your hand. Hello.
Sir, good afternoon. Am I audible?
Yes. Good afternoon. Yes.
Sir, there was a doubt regarding the bipartite graph that is classified as class 1. So these are the one-way theorem, right? I can't say like if the graph is not bipartite, then it is not class 1, right?
Yes, these are one-way theorems, right?
Okay. And sir, other doubt was, sir, I just need to like go through the 3n minus 6 and 2n minus 4. So if possible, can I ask those doubt tomorrow? Like I need to go through these topics again.
These two proof, right?
Yeah, actually I had understand the proof, but there was like, I guess there was one previous year question which consists of like taking the delta and the big delta into consideration.
See, the GATE exam will create questions. Like
Yes,
they are
sir.
not going to ask, they are not going to ask from goclass's notes. Okay.
Yes,
They,
sir.
that's not what they will do. They will create their own questions. But the concept that we have understood, you have to apply these concepts. This is what I'm saying. Like in after the GATE exam, once you come out of the GATE exam, I promise you one thing, that you will guarantee that every 65 questions, every concept we have seen, every concept.
Yes, sir.
Okay. So by the end of this year, like we are going slowly, but we have time. We are going slowly because we have time. In every lecture, I am taking many examples, many variations, many questions, small points. Okay, all these things I am doing because the reason is because we have time. So we can prepare in a very nice manner. And
Yes, sir.
after September, for the next 4 months, October, November, December, January, for 4 months, we will do a lot of practice. Okay, so
Yes,
much
sir.
practice we will do that GATE exam will become like a two stable for you. It will become like a, I can guarantee like it will become very easy for you. You will feel very confident in the GATE exam. Anyway, what I'm saying, in the previous year GATE question, when you solve, then there can be some questions which need the concepts. You have to apply your brain. You have to apply your analytical skills. Okay, so that you can do. But the proof I have told you, like this E is less than equal to 3V minus 6. This proof I told you, and the proof is very simple.
Yes,
Should I
sir.
tell you the proof or do you understand this?
Understood, sir. Understood.
Yes, this proof is very easy because this proof is like this. See, okay, quickly you can do. If you want, you can do quickly. So you have planar graph, but very important that this will only happen for planar graph. So if you have a planar graph which is connected, these things will happen. These two results are only for connected planar graph where number of vertices is greater than equal to 3.
Yes,
Then
sir.
what do you know? You know that
B plus F equal to
degree
E
of
plus
every
2.
face will be, yes, tell me. Yeah, you tell me. Degree of every face will be,
Sir, it greater than equal to 3.
yes, because it will happen because you have at least three vertices, and when you have at least three vertices like A, B, C, and this is a connected graph. Okay, so whatever you do, you cannot get a 2 degree face. You cannot
Yes,
get
sir.
a 2 degree face. Like whatever you do, you cannot get a 2 degree face in
Yes.
connected planar graph where number of vertices is greater than equal to 3. You cannot get a face with a 2 degree. You cannot get,
Yes, sir.
because if you want to get a 2 degree face, then this is the only choice.
Yeah.
This is the only graph where you have a face with a degree 2.
Yes, sir.
This is the only graph. There is no other graph where you have degree of face is equal to 2. This is the only graph where you have a face with degree 2. Every other graph, if you take, then degree of face will be greater than equal to 3. Now what?
Equal to 3.
So this is what you have. Degree of every face is greater than equal to 3. And you know what is total degree?
Twice the number of edges.
Total degree of faces, that is equal to twice the number of edges.
Yes,
So
sir.
if I take this minimum degree, like I can say this is the minimum degree of face. So if
Yeah.
I number of faces is f, and if I make this 3 into f, like if I take this minimum, then what will happen to the balance? To the
Less than
balance
equal
of
to
this
2.
equation? Huh?
Less than equal to 2e.
Yes, very good. Because this balance will basically, it will this balance will happen like this, right?
Yes,
Okay.
sir.
Now what happens? So 3f is less than equal to 2e. That is very good, very good. Now you can apply, you know that this is connected planar. So Euler formula. What
V
Euler
plus
says?
equal to
Euler
V
says
plus
that
F
v
equal
plus
to,
f is equal to e
sir.
plus 2.
Yes, sir.
So what you do, you put it. And we want a relation between v comma. So you replace this f. So from f is v minus e minus v plus 2. Now you put this f here. This you put here. So
6.
what you will get? You will get a 3 into this is less than 2e.
ठीक है. Yes, sir.
This is less than 2e. So from here, what you will get? Now you can just check it out. So here you will get e is less than equal to 3v minus 6. You can just check it. You can just check it. This will be like minus 3v.
3 sir 2 साइड ले जाएंगे माइनस हो जाएगा and then 3 minus 6.
Right. So okay. So this is your proof. Isn't it very simple? Like very simple.
Yes, sir. Got it.
The same thing you can do for the another. If you have triangle free graph, then what will happen? Like if
Minimum
your
degree will
triangle
be 4.
if your graph is triangle free, now you cannot get degree 3 also.
Yes, sir.
Now you cannot get degree 3. See, very simple point. If you want degree 2, then what you need? If you want degree 2 face, if you want, then degree 2 face if you want, then only chance, only graph is this. Only graph is this. This is the only graph. This K2 is the only graph. This K2 is the only graph where you have degree 2 face. And if you want degree 3 face, you want a face which has degree 3. It means what? It means this is surrounded by 3 edges.
Yes, sir.
It means it is surrounded by 3 edges. So if you don't have triangle, then it means there is no degree 3 face. So the degree of face will be greater than equal to 4. Now
Yes,
you
sir.
can apply this. So it will become 4f less than equal to 2e. Now it will become 4f less than equal to 2e. Okay, 4 into this.
4.
So from
Yes,
here,
sir.
what you will get e is less than equal to, from here you will get e is less than equal to 2v minus 4.
2v minus 4.
Okay.
Yes, sir.
Any other doubt?
There was a doubt regarding the way we are computing the edge coloring. So in case we have 3 vertices or greater than equal to 3 vertices that have the same maximum degree, then we cannot comment like the edge coloring will be delta plus 1, right? We have to
Yes.
manually go through.
Yes, we don't have to manually go through. In the GATE exam, see, these edge coloring, all these numbers, all these graph number, every graph number, chromatic number, edge chromatic number, independent set, vertex cover, matching, all these graph number, these are very complicated things. These are not easy. These are all these are NP hard problems. NP hard means we don't have efficient algorithm. Okay, like if I give you a random graph on 7 or 8 vertices, if I give you a big graph, complicated graph, if I give you, then you cannot find. Okay, so the GATE exam will not ask it. The GATE exam will only ask those questions where you can solve the question very easily if you understand few things. Okay.
Yes, sir.
So like you can notice this GATE 2020 question in edge coloring. So for that question, very simple fact you can apply. Okay, very simple. Just there was unique vertex. There was only one vertex of maximum degree. And you know that if there are less than 3 vertices of maximum degree, then that is your class 1.
Yes, sir.
Very simple. And similarly, you can see like bipartite. If your graph is bipartite, then it is class 1. If your graph is regular with odd degree vertices, regular with odd number of vertices, then it is class 2. Okay. So like this, all these things you can apply. And if all these things do not apply, if you have a graph where all these things do not apply, like all these things are one way, if you cannot apply all these things, then you go manually.
Okay.
Okay.
Yes, sir.
Any other doubt?
No, sir. All set.
Okay.
Thank you, sir.
Okay. Thank you, everyone. Thank you.